Let's start the morning session. The speaker is Dennis Gatesbury. We'll speak about the stack of local systems with a strict variation and geometrical nets with an importance in support.
Thank you very much. Thank you very much for the invitation. It's a real pleasure to be here. All right. Without further ado, so this is a joint work with Arinkin, Kazdan, Raskin, Rosenblum, and Warszawski, and it talks about a new paradigm in which geometric language takes place, and this paradigm has a direct connection to the classical theory of automorphic functions, unlike the previously existing versions of geometric languages. So, but I start by reviewing the previously existing versions. So the first one is what we call the de Rham version. Is it visible?
Yeah. It is, but it's better if you write bigger.
Even bigger. Okay, I'll try.
And can you speak up?
Also, yeah. Yeah. Sure. Yes. So that's the. So we'll start by reviewing the de Rham version. The de Rham version takes place over an arbitrary ground field of characteristic 0. And so in all versions, we fix a curve X over our ground field, and a reductive group, and the reductive group is also over the same ground field. And the basic object of study on what we call the automorphic side is the following. We consider what we call bund G. It's the moduli stack of principal G bundles on this curve X. So that's the automorphic space, and in the de Rham version, we study the category of D modules. So when I say categories such as D modules or quasi-coherent sheaves, I always mean the corresponding derived category. So everything in this world is derived. And so the feature of the de Rham situation is that this category is linear over the same field K as our geometry is defined over. So it's a K-linear category. So this is a category of interest on the automorphic side. So now I'll explain what happens on the Langlands dual side. So we consider the stack. So we consider the Langlands dual group, G check, and in the de Rham setting, here it's very important, it's also a reductive group over the same ground field. So that would be different in different contexts. And we consider the stack of local systems with respect to the Langlands dual. And it's an algebraic stack, again, over the same ground field. And in a few minutes, I'll remind you the definition of the stack. So, but this, whatever it is the usual stack of local systems in the de Rham world. And so,
local systems on what?
On the same curve. On the same curve. So it's very important. Like in classical Langlands, we're talking about some global field which is played. So Rho is played with this algebraic curve. And so somewhat naively, the category on the what we call Galois side consists of quasi-coherent sheaves on this stack. So this is not quite the right category we want to consider, but on the first pass, let me just write that. And the geometric Langlands conjecture in the de Rham setting says that these two guys are supposed to be equivalent. And so this has been, okay, so before I state it, so this is, as I said, not quite correct. And instead of this, one has to make a tiny correction, and what I write int coherent sheaves with nilpotent singular support. But whatever it is for the most part of the stuff you can ignore it. It's a correction that has to do with the fact that the stack of local systems is not smooth, like Bungee, but it's singular with it's a locally complete intersection in the derived sense, and so we have to distinguish between coherent complexes and perfect complexes, and this is what takes, so this modification takes that into account. So the naive guess was around for some 30 years. It was what Balance and Rinfield called the best hope. So this formulation, but it was known to be incorrect. It was known that something didn't quite add up. So this correction, so this category and this formulation of the conjecture was proposed around 2013, and it has been open since. And now we are super close to the proof. So like the main mystery of why this is supposed to be true has to do with non-vanishing of Whittaker coefficients has recently been cracked by Raskin and his PhD student Fagerman. So it's not a theorem, but it's very close. For example, it's a theorem already for classical groups. So this is the Durand version of the Lagrange correspondence. So now I'll flip the page and I'll explain the Betti version. So in this case, our ground field is complex numbers. But we worked with sheaves with coefficients in vector spaces over an arbitrary field or characteristic 0. Let me call it E. So our X is still over the ground field, and we consider the same geometric object Bungee. And we now consider the category of sheaves of E vector spaces. So this is an algebraic stack over C. We turn it, well, if it were algebraic right, it would turn it into a topological space and consider all sheaves in it. So topological sheaves.
In analytic topology.
In analytic topology, but this definition also makes sense for stacks. So this is not quite the category that we want to consider, but I'll write it on the first pass. So let's see what we have on the spectral side. On the spectral side, we still have the stack of local systems on X with respect to G check, but one has to be careful. So G was an algebraic group over K, but G check we regard it as an algebraic group over the field of coefficients. So these are local systems of E vector spaces. So this is an algebraic stack over the field of coefficients. Let me write it kind of E, so it's a sheaves of E vector spaces. And we consider the category of quasi-coherent sheaves on it. And this is a linear category over E. So on both sides, our categories are E linear. So in the Durand setting, both sides were K linear, and K played this dual role of both the geometry and coefficients. Here they're separated. And as before, so one has to make this replacement. So write in co-nilp but you can ignore it. And on the first pass, you would want to compare, to say that these two categories are equivalent, but this is not true by a very kind of large amount. And it was, so you can take the case when G is a torus, and you'll see how far off you are, and what you will discover is the following, and it was a discovery of David Ben-Zvi and David Nadler, is that, so you should consider not all sheaves, but sheaves with prescribed singular support. So, namely, if you have an algebraic variety, well, let's say over C, and you can consider its cotangent bundle, if you have a subset, it makes sense to consider sheaves with singular support contained in this subset. So this is a definition due to Kashivar and Shapira. So it makes sense to consider, let me call it, sheaves sub n on Y as a full subcategory inside sheaves on Y. If I write here, will that be visible? Or, okay, let me just flip the page. So in our case, our Y is Bun-G, and T star Bun-G is known as the space of Higgs bundles on the curve. And so let me say what it is, for example, when the group is GLN. So if G is GLN, so Bun-G classifies just rank n vector bundles on the curve. And Higgs classifies pairs, a rank n vector bundle, and a Higgs field, where A, so it's a Higgs field, it's a map as coherent sheaves from M tensor the sheaf of one form, so my curve. So why am I saying this? So that if you look at this A, it makes sense to require that this A be nilpotent at the generic point of the curve. So if you iterate it n times, you get 0. And so you can explicitly write what Higgs is for arbitrary group G, and it has similar description. And in any group, it contains, in fact, the Lagrangian. It's called the nilpotent cone. And so going back to the Betty version, so one has to consider not all sheaves, but sheaves with nilpotent singular support. But these sheaves in the Betty setting are not constructible. So they have nilpotent singular support, but they may have infinite dimensional fibers. And again, Langland's conjecture in the Betty setting says that these categories are equivalent. And again, so in fact, these conjectures are interconnected, although one is in the de Rham setting, the other is a Betty setting. You don't have Riemann-Hilbert because we are outside the constructible world, but in fact, one can show that the de Rham version implies this version. So that is to say, this is also very, very close to being a theorem now. So, and finally, so let me just emphasize this is Betty version of the stack of local systems. And even, so here was the de Rham version. And even when this K is equal to C, so both the geometric objects are algebraic stacks over C, they are different. They're different as algebraic stacks, they become isomorphic after analytification. All right. So, and now I'll describe the new version, this restricted version. So the advantage of the restricted version is that it makes sense in any sheaf theoretic setting. So K will be an arbitrary ground field. And we'll consider one of the following three sheaf theoretic contexts. So it'll be either, I'll go de Rham, but, so what I'll write sheaves, I will mean in the holonomic D-modules. Well, let me just say holonomic D-modules. So technically speaking, my categories are large. So holonomic D-modules is a small category and they're int-completed. Again, if you don't know what it is, just ignore it. Or I consider Betty, and let me just here, just to be consistent, I'll write sheaves Betty. So, to emphasize that I'm considering all topological sheaves. I'll still write sheaves, but I'll mean constructible sheaves. So, okay, thank you. So, this makes sense in arbitrary ground field of characteristic 0, and this category is still k-linear. This, as before, makes sense when the ground field is complex numbers, and the coefficients can be an arbitrary field of characteristic 0. And finally, there is an étale version, and I'll write sheaves for constructible sheaves. So here, the ground field is arbitrary, but the field of coefficients is QL bar. So let me say that E is K, here E is arbitrary, and here is QL bar. And so what I'm going to say, I'll use sheaves to mean one of these three guys, and I'll be insensitive to which precise of these three, which of these three contexts I'm using. All right. So now let me explain this restricted version of the Langland's conjecture. So on the automorphic side, I still consider Bun-G. It's the same object as before, and I write sheaves to mean one of these three categories, depending on the context. But just as in the Betti context, I'll write nilp. So it's sheaves with nilpotent singular support. So as I mentioned, in the Betti setting, this is a notion developed by Kashewar and Shapira. In the Durham setting, this is a notion which was developed by in the 70s by Sato. And the étale setting, especially in characteristic, when the ground field has characteristic P, this is a relatively new version. And it was a discovery of Bellinson some 6 years ago that it actually works. So that one can make sense of singular support also for étale sheaves. And so for that reason, this category makes sense on the automorphic side. And now let's see what we want to compare it to on the Galois side. So let me write that it's restricted. So I'll write the same symbols. So I'll write int co nilp, which replaces quasi-co, forget that. But so here a new geometric object will appear, and I'll write it log sys g check restricted. So it's a new beast whose definition I'll explain in a moment. And so the Langland's conjecture in the setting will predict that these two categories are equivalent. So the fun of this game is that, so it's restricted, it's much smaller equivalence. We're talking about much smaller objects, so the beauty of this game is the following, that, so
in the Betti case, this is no restriction because you had open already.
So it's different kind of sheaves. So before it was all topological sheaves, and here are the int constructible guys.
I see, okay, thank you.
And I'll explain that when I'll be talking about local system, how local system Betti differs from this. And you will see the difference. So what happens is that this Durham version contains this as a particular case. But in fact, you have the implication in the opposite direction. So you would seem that this is much stronger, but in fact they're equivalent. And also Betti. It implies, but in fact they are equivalent. And as I'll explain at the end of the talk, so restricted version, when your ground field is algebraic closure of the finite field, this version is directly related to the classical theory of automorphic functions. All right. Let me pause for questions.
So I didn't quite get the punchline. This local system restricted guy, it's a different modular problem.
It's a different modular problem, which I
Which
will
you're going
now
to
explain.
Yeah, yeah. Also, on the previous things you mentioned that responses this have this Ram and Betty big versions, in one place and another. But I don't really
So
believe it.
no, they don't.
They don't. Yeah.
They don't. What happens is that
This is kind of Riemann Hilbert. Is this Riemann Hilbert?
yeah. So the Ram over arbitrary k is equivalent to restricted.
Yeah.
Betty with over C with arbitrary E is equivalent to restricted, but restricted guys are equivalent by means of Riemann Hilbert.
I think
So basically, you prove this, you go restricted, apply Riemann Hilbert, you go here. That's how this implies this.
But which Riemann Hilbert? Is this non-holonomic Riemann Hilbert?
Yeah. So restricted. So restricted talks about holonomic.
And holonomic will
Just the standard Riemann Hilbert.
So standard Riemann Hilbert. So holonomic, there are two versions: holonomic and holonomic regular singularities.
Yeah.
However, one of the main theorems in our paper shows that all objects here in the holonomic version automatically have regular singularities.
Okay.
It had been conjectured by Bellens and Ginfeld, but
Okay, yeah.
you can prove it.
As it's complete.
Yeah. It's an important technical point. This side of the room, you owe me a question.
Okay, so there's a right-hand side, a left-hand side. The restricted Duram, what was this called? It's automorphic side?
Yeah.
The restricted Duram automorphic side and the restricted by the automorphic side are themselves equivalent by
Riemann Hilbert.
Hilbert.
Correct. Modulo the result of the mentioned that the holonomic guys happen to have regular singularities automatically. This side of the room. Give me one question. Anything.
Are you going to explain? I mean, usually in the original Betty version, there's a very big object.
Yeah.
And also in this drum. Are you going to explain actually how this backwards arrow works?
Does it be in question time? It's a fun thing. It's like juggling field extensions, and very coincidental field extensions. Some algebraic trick.
Or maybe just it's anticipating all these things which you explain because it's kind of restricted. Is it something to have like some algebraic variety and replaced by disjoint union or formal neighborhood of?
Did you see the definition? Did you guess?
No, I guess.
You're right on.
Okay. Okay.
Okay, I will. Exactly right. All right, so let me remind the definition of Lox's Deram, Lox's Betty, and then I'll pass to the definition of Lox's restricted. So maybe I'll first do Lox's Betty. I'll write the group G check because that's what the group is. And again, my geometry is over C and my field of coefficients, arbitrary field characteristic 0. And here's how you give the definition in Tannakian terms. So it's an object of algebraic geometry, so we have to say what hom from a affine test scheme is. So from spec A to this Loxis. So, and what we say is the following. These are symmetric monoidal functors from the Tannakian definition, from the category of algebraic representations Rev G check to the following thing. So what you do, you write A modules inside the category of Betty sheaves on the curve. In other words, just consider Betty sheaves with an action of A by endomorphisms. That's what they are. So I have to warn you that this is an object, everything has to be in derived algebraic geometry, so A is not a classical ring, it has to be a connected DG ring. And in this case, you have to talk about functors that are right exactly with respect to the T structure. You can safely forget it for this discussion.
G-check is linear representation.
Pardon me? Yes. So, in the Betti context, G-check is a group over E. So all of this is like E-linear categories. Exactly right.
You can think about rational numbers.
Pardon me?
Beta checking rational numbers.
E, yeah, and the rational numbers, absolutely. Let me just say.
Analytic numbers and,
Pardon me?
like you use analytic numbers in Italian, I think you can use rational numbers.
Yeah. Let me just say that you can actually replace this target by something smaller to make it more manageable. So you can see that this such a function automatically lands inside the subcategory of A modules inside locally constant sheaves. By the way, locally constant, instead of writing locally constant, I could have said the singular support condition, meaning the zero section, which are also the same as A modules inside, well, just Betti local systems, as you know them. In other words, these are just representations of the fundamental group on E vector spaces. But these E vector spaces are infinite dimensional. And so when I write A modules, you can just say the same thing. These are just representations of the fundamental group on A modules. So fix an A module and have an action of the fundamental group on it. So that's what these things are.
So it's just a tensor product, A group ring of the fundamental group.
Absolutely. And here it's an important condition is that, so these local systems, as local systems of E vector spaces are infinite dimensional. And so they have an action of A. So that's the definition in the Betti world. So now I have very conveniently the second whiteboard, and let me contrast it with the Durand definition. And it's again symmetric monoidal functors from the same source. Two A modules inside D modules on the curve. And let me just say that there is nothing you can replace this by. Well, you cannot say that it lands in, these are D modules, that's it.
What is written there?
Pardon me?
Is it A module and there D modules?
It's A modules within D modules. So these are D modules with an action of A. That's what it is. All right, and finally, let me give the definition of the restricted version. And I'll contrast it with these two. And again, the restricted version comes in these three different flavors, but the definition is the same.
But I still didn't understand which thing was local system.
So if you have such a symmetric monoidal functors, the claim is that the sheet you get is automatically locally constant. So I'm saying that instead of this ambient target category, you can replace it by just smaller category, just locally constant Betti sheets. And what are those? Those are just representations of phi 1, but infinite dimensional. Yeah? Okay?
Well, why should it be locally constant?
If you wish proof, so every object here is dualizable. So this thing admits a dual that forces it to be locally constant. Yeah. Finally, I'll define the main object of interest, this local system restricted. So, and it's the same thing, symmetric monoidal functors from the same source category. And I'll write A modules. And here I'll write this sheaves. But here it's, again, important to remember who the sheaves are. These are inconstructible sheaves. And so let's contrast.
Did you want to write restricted or?
Oh, sorry. And I cannot replace restricted. So let's contrast this definition with these two. Like, for example, suppose you are over an arbitrary field of characteristic 0k. Let's see how this is different from this. The difference is the target category. Here, it's A modules within arbitrary D modules. So if you forget the A module structure, your underlying D module may be like D, or kind of multiple copies of D. And here, your underlying D module must be the union of holonomic guys. So by the way, here, like in this context, you can replace equivalently by A modules within, let me call it lease. So these are unions of local systems of finite rank. Like here, this dualizability forces you that your sheaf is automatically, well, as I said, lease. In other words, a local system, constructible local system, but you allow unions of such. And so let's see the difference. So like the underlying D module here is arbitrary, and here it's very restricted. So you're not allowing anything that looks like D. It must be a union of finite rank local systems.
But if you consider finite dimensional representation of object would be finite.
Pardon me?
Yeah, but I consider int objects.
Because A.
A, yeah.
Yeah. So A is maybe. So if A was Artinian, you would not see any difference.
Yeah.
But A may be full dimensional, and it forces. Yeah. So the rank as an E vector space is infinite. And also, let's contrast this definition in the Betti setting. So your ground field is complex numbers. So here's the difference. It's A modules, but here, these are all Betti local systems. They are infinite dimensional representations of pi 1. In particular, if representations are not locally finite over pi 1. And here, we have my representation is supposed to be the union of locally finite ones.
Can we in this game just restrict to A Artinian?
No.
Restricted?
So that would be this disjoint union of formal completions.
Yeah.
And this guy, I'll say what it looks like. So that's the whole point. So let me give an example of what this thing looks like. So let us be over C, and in this case there are two versions. So in this case there is log sys Betti. It's kind of a very classical object whose definition was on the previous page. And so it's known to admit a coarse moduli space. Call this map R. So Betti coarse. And so it's an affine scheme whose points are in bijection with semi-simple local systems. And what this map does, it collapses. So 2 points here go to the same point here if and only if they have the same semi-simplification. So this fiber is just
Still G-check though.
G-check, yes. This map remembers the semi-simple conjugacy class. And so what you can do now is the following. Let me write log sys restricted course. And this is exactly what Maxime said. So this is the disjoint union of formal completions of all points. And this log sys restricted is the fiber product. And what this means is this. So here is, in the Betti setting, here is a concrete description of what this guy looks like. You fix a semi-simple local system, and you consider the fiber of this map. And these fibers are different depending on what the local system was. If your local system was not only semi-simple, if it was irreducible, then the fiber is just one point. But if your local system, if your local system was trivial, the fiber is full dimensional. You take the fiber and you take its formal completion, and you take the disjoint union of such of all isomorphic classes of semi-simple guys. So that's what this guy looks like. It's huge disjoint union. However, some fibers are full dimensional. And because some of them are full dimensional, it was important to consider these A's that are not Artinian. So Maxim, I think that answers your question of what it looks like.
Yeah, but it's kind of like a very cheap way to get.
Exactly.
Yeah.
It's a very cheap way to get the modular space, and that's why this object was ignored.
Yeah.
However, so let me quote a theorem that tells you that's kind of first theorem in this direction that tells you that this is a sensible object. So I'll quote 3 theorems.
Can you explain what these objects were?
Say again?
Can you say again what these objects
So this is the modular space.
These ones I understood. What were the other
So
ones?
this guy is the following. You take all closed points, and you take the disjoint union formal completions of these closed points. And you take the pre-image. In other words, it's a disjoint union of all semi-simple local systems. Take the fiber over each and take its formal completion.
And the statement is that this represents whatever functor.
Yes. Yeah, in the Betti setting. And in the Tal setting, you don't have this, you only have that. All right, so here is kind of the first bunch of theorems. So first I quote some known results. So first, so first, this is Betti, and this is Nadler and Yoon. And it says the following, that if you consider this sheaves Betti, so it's a step towards geometric Lagrange. So it's not full equivalence, but it's an important step towards it, that it carries a monoidal action of the category of quasi-coherent sheaves on the stack of Betti local systems. So remember Langland's conjecture as I stated it. Where was it? It was here. It stated that this category is equivalent to some modification of this quasi-co. And here it says that this quasi-co acts on it in a monoidal way. And this theorem is fairly simple as far as such things go in this theory. So there is a Durand version, and this is Drinfeld and myself, and it says that if you consider, so this, so it's a spectral decomposition theorem. It says that this quasi-co in the Durand version acts on the category of D modules. And this is a crazily complicated theorem because, I mean, it uses representations of affine algebra at the critical level. And finally, let me state the restricted version. And it kind of justifies why this local system restricted is a sensible object. So, and it's new, so this is from our paper. So and although this system restricted may seem like a naive object, it's kind of a cheap fix, as Maxim said. Nonetheless, you can show that this category acts on sheaves nil. And so there is a cheap way to prove this theorem, but the honest way to prove it, it becomes a complicated technical theorem. So this kind of justifies why this object is not so stupid. So corollary of this theorem, that if you have two local systems, let me say, a pair of G-check local systems with non-isomorphic semi-simplifications. So there is a notion of Hecke eigensheaf for each of them, and then the claim is that if you take two Hecke eigensheafs, one for sigma 1, one sigma 2, there is no harms between them. So in other words, the category of sheaves with important singular support split as a direct sum according to isomorphic classes of semi-simple local systems.
Equal to 0. No?
Sorry. Equal to 0. So that's a pretty strong result. That it says that in kind of the spectral decomposition of the category of sheaves with important singular support.
Why, I mean, there's two parts of spectral decomposition. One is that if you have things in different, like orthogonal, and then there's a statement that you can, in fact, split any one into some.
Both are contained here. So this stack is disjoint union of a class of semi-simplification. So each class of semi-simplification gives you an idempotent.
Yeah.
And act by this idempotent that will single out a direct tangent of the categories.
I don't understand this corollary. I mean, what if they are non-isomorphic semi-simplifications, but they have an isomorphic piece? You mean none of the pieces are isomorphic?
So these are G-check local systems.
Okay.
So you have this system of eigenvalues, and there are not only non-isomorphic, there are non-isomorphic after semi-simplification. Then the Hecke eigensheafs for them don't talk to each other.
Tony is complaining about your grammar.
Yes, so tell me, yes, please ask again.
Right, you say non-isomorphic semi-simplifications.
Yes.
That what I understand as there is a piece in the semi-simplification in one that's not isomorphic to a piece of simplification.
No. So you're talking about GLN.
Yeah, say.
Yes. Yeah. And what I mean is non-isomorphic.
Completely not.
No.
Just
Non-isomorphic. Like if there are some pieces in common, it's okay.
Okay.
If not all pieces are the same, if not all pieces in the semi-simplification are the same, then the eigensheafs don't talk to each other.
Then the eigensheaf comes.
I'm saying stronger than you're saying.
Okay.
But your statement, having pieces in common, only makes sense for GLN, so you would not be able to make sense of your statement for an arbitrary reductive group,
Okay.
just non-isomorphic as is. So, Maxime, does it kind of explain why this object is not as naive?
I understand.
All right.
And what is the thing on the right-hand side on which you're acting?
This
Yeah.
is my category of inconstructible sheets with important single support. This is my object.
Yeah, and in fact, this reminds like people try to construct a hot structure on a deformations of a given variation of hot structures and conformal completions. Yes, so you consider
I want to know more about this.
like Hayne and something.
So we should talk about.
Yeah,
I want to know more. All right. So this wraps up two parts of my talk. So my last remaining part will be the connection between this category and the classical theory of automorphic functions. Let me see how I'm doing on time.
We have 15 minutes.
Okay. All right. Forget everything that I said. So from now on, K will be FQ bar, and we'll consider my category sheaves with an important single support on bund G. Again, inconstructible sheaves. So this is my category of interest. It's a category linear over QL bar. However, I'll assume that my curve and my group are defined over Q. So this object carries an action of the geometric. So bund G carries an action of the geometric Frobenius, And there's Frobenius pullback that is an endofunctor of this category. Frobenius push forward, like it better. Okay, so now let me remind you of the following general procedure. So as you know, if you have a finite dimensional vector space and an endomorphism, you can take its trace. So let me remind you the definition of trace. So if you have a finite dimensional vector space, it admits a dual. So it admits something called V star with an evaluation map to your ground field and the unit map. So this is co-unit, and this is the unit. And so if you have an endomorphism, here's how you calculate the trace. The trace is a scalar, and what you do is this. You apply the unit, and so T is the endomorphism. You apply this endomorphism along the first factor, and then you apply the co-unit, and the composite is a scalar. So that's a trace. Now, this definition makes sense in an arbitrary symmetric monoidal category and a dualizable object. So if O category, and if little o is a dualizable object,
It's kind of already converted to definition of trace. You can make this have endomorphism with element of V cross V star. Yeah, it's
yeah, and it's a dualizable object, and if T is an endomorphism of little o inside O, you can create the trace of T on little o, and that's an endomorphism of. Okay, now I have to see if the audience is awake. The trace is what? Maxime is barred from answering this question. I need the audience to wake up and tell me the trace in a symmetric monoidal category is an element of what?
You're blocking the answer right now.
it was
It was like endomorphism of that.
Yeah. It's an endomorphism of the unit object. And the way it's defined is exactly the same. So dualizable means that you have the unit map, then you apply your T, and you compose the edit.
I still complain. It's doesn't T gives a morphism from element morphism from unit to or to.
Say one more time.
No, does this endomorphism gives an element of or dual tensor O?
No. So T is an endomorphism of little o?
Yes. It doesn't give an morphism from identity objects to.
It does. That's one way to interpret it.
It's kind of more straightforward.
Yeah.
To this long
I mean, it's the same. It's all the same. So, however, who is my O? So my O is what we call DG categories. So such as sheaves on something. And so the world of DG categories is symmetric monoidal by this operation of tensor product. And so an example is the following. So Maxime, you were one of the people who discovered it, right? Tensor product of categories, no? I can't remember. So, example. So if you have one DG category which is modules for some associative algebra A1, and you have another which is modules for some associative algebra A2, then the definition of tensor product of DG categories is rigged in such a way that this tensor product is modules for the tensor product of algebras. So in particular, so corollary of this example is that if you have two reasonable algebraic stacks, if you consider quasi-coherent sheaves on Y1, tensor quasi-coherent sheaves on Y2, this will be quasi-coherent sheaves on Y1 times Y2. And similarly for D modules. So another example of tensor product, and it's more involved, happens in topology. If you have reasonable topological spaces, then sheaves on, let me call them y1 and y2, Betty sheaves, topological sheaves. On y2, the external tensor product maps it isomorphically to sheaves on the product in the product topology. The product topology, topological space is rigged so to have this happen. So, however, here is what is false. So, non-example. So if you consider sheaves as we define them, this int-holonomic or inconstructible or elatic sheaves it maps to sheaves on the product, but this is not an equivalence. All right. So now what we'll be doing, we'll be taking the trace construction in the world in this symmetric model category. As I said, to apply the trace construction, my object needs to be dualizable. A way to guarantee that a DG category is dualizable is that it's compactly generated. And believe me that, so it's a non-trivial theorem that this category of sheaves with important singular support is compactly generated. All right. So the two things we can consider. So if Y is stack over FQ bar, but defined over FQ, you can consider the Frobenius endomorphism of Y, and you can try to compute. So you can consider Frobenius push forward. And you may want to compute the trace of this Frobenius push forward on sheaves on Y, elatic sheaves. So now you can unwind Grothendieck's function to sheaf correspondence, and you'll see that, so this is a vector space. So this is, our formalism said that the trace is an endomorphism of the unit object of my category. My category is DG category, the unit object is the category of vector spaces. And endomorphism is again vector spaces. So this is a vector space, and Grothendieck defines as a map from here to the vector space of functions on FQ points. But, so I don't have time to explain it. I'll be happy to do it in kind of question time. The claim is that this map is hugely not an isomorphism. So, like, the fact that this fails to be an isomorphism implies that this map fails to be an isomorphism. So, the Hochschild homology of Frobenius push forward on the category of sheaves is much, much bigger than the space of functions. However, so here comes the main theorem of our work. And so it says the following. So this is AGK RRV. So it says the following, that so we can consider the trace of Frobenius push forward on the category of all sheaves on band G, and as I just said, this map to the space of functions. So here, if Y is not quasi-compact, you actually map to functions with finite support on band G of FQ, and this is the classical automorphic space. So we have this map is very far from being isomorphism. But if you precompose it with the embedding of sheaves with nilpotent singular support, so if you consider the trace of Frobenius not on all sheaves, but specifically on our subcategory, so that this composite map is an isomorphism. So this is the main theorem of our work, And it says that, so it's kind of the first direct connection between the geometric theory and the classical theory. So this is the space of unramified automorphic functions as we know it. And the claim is that if you take this category of automorphic sheaves with nilpotent single support, just as an abstract category, with an action of the Frobenius, the Hausdorff homology of this Frobenius endofunctor recovers the space of automorphic functions. So it's a strong assertion. It says that if you can prove something about the structure of the category, you can deduce assertions about the space of automorphic functions. So until this theorem, the passage from the geometric to the classical was kind of element by element. So to a particular sheaf, you assigned a particular function, and you could prove the existence of some functions by proving the existence of sheaves, but that's where the story ended. Here, we can prove something about just the overall structure of the space of automorphic functions. So now let me conclude my talk by coupling this isomorphism with the geometric Lagrange conjecture. Let me actually stop for pause for questions. Am I out of time already? 5 minutes.
I thought Chavatara was supposed to tell you that this is at least close to an ICMS.
No. So Chavatara talks about semi-simplification of semi-simple objects for one thing. But still it's really far.
What does Chavatara tell you in this language?
So here's what it says. So if you have two irreducible perverse sheaves in algebraic variety, such that the trace functions over not your FQ, but all its line extensions are equal, then your two irreducible perverse sheaves are isomorphic.
Yeah.
That's what it says.
Okay.
So here it's a particular FQ.
I see. So they took all FQ, they took all the extensions.
Yeah, but it's also only after semi-simplification.
Oh, yeah.
So let me finish it by coupling this isomorphism with the geometric Lagrange conjecture, the restricted version. So let me remind you that that statement said that this category is equivalent to this int-co nil of log cis restricted. And its equivalent carrying the Frobenius. So therefore, if you believe in this equivalence, it will say that the trace of the Frobenius in this category is equal to the trace of the Frobenius in this category. And if you can compute it, you will give yourself an expression for the space of automorphic functions purely in terms of Galois side. So if it were not int-co nil but quasi-co, and here is the first time in this talk that the distinction becomes important. So in general, if you have an algebraic variety Y with an endomorphism, the trace of the upper star of quasi-co Y is in general global sections of the structure sheaf on the space, on this stack of Frobenius phi fixed points. So, and let's introduce the notation. So let me call log cis arithmetic. It's Frobenius fixed points on this restricted guy. And so we stipulated this is the stack of arithmetic local systems. So if you are searching for what it means, algebra geometric object that pacifies arithmetic local systems, we stipulate that this is that. So this is some of the object that Vincent Lafort did not have in his talk, so he kind of, in his work.
Sorry, what does it say on the left-hand side?
So the stack arithmetic local system is this Frobenius fixed points. And again, one can take Maxim's objection saying that this object is kind of naive. And so you take Frobenius fixed points, you may still get something naive. However, so let me just say that Scholze and Shin-Wanzhou independently defined their respective versions of the stack, and they happen to be the same. So the three definitions are different, but the definition is different, but the geometric object is the same. So basically, the existing approaches to defining this object yield the same result.
You still get here many isolated points corresponding to reducible.
Finitely many.
Finitely many. And get some varieties. So.
Yeah. So this. So let me just state the corollary of conjecture. So again, combination of this theorem and the geometric Langlands conjecture, taking into account the distinction between int-co and quasi-co. And it says the following, that the space of automorphic functions is isomorphic to the following. So if it were quasi-co, it would be just global functions. But here, it's not quite that. So we're taking log-sys arithmetic, as we know it, but instead of global functions, we're taking sections of the dualizing sheaf. And the distinction is pretty huge, namely this second arithmetic log systems, it's not a complete intersection. So an object of derived algebraic geometry, so your structure sheaf goes infinitely off to the left, and the dualizing sheaf goes infinitely off to the right. So this O is very different from omega. And so you will not see it on irreducible local systems, but when you hit something like Eisenstein series, where all the analytic difficulties appear, so you will see the distinction. So this is the kind of the first prediction. So if you want to say what Langlands conjecture says that automorphic functions can be expressed in Galois terms. What does it mean? So in fact, it means exactly that it's sections of omega on the stack of local systems, arithmetic version defined in this way. All right, and I'm done.
Questions? I have several questions during the talk. Yeah, okay.
You go back a page or
This one?
So, as you mentioned, functions only see semi-simplification. But this other one seems like how is the thing over here seen? How has it been semi-simplified?
No, so the semi-simplification happens, it's different from Chibodera.
But how can functions see anything other than semi-simplification?
Can you say the question one more time, please?
So I would have thought that functions on Bungie can only see the semi-simplification of sheaves.
Yeah, so this is Hochschild homology.
Ah, okay.
I mean, it's a category,
Yeah, I
and
see.
the function is taking Hochschild homology.
Yeah, I see.
And like objects of the category, compact objects of the category give rise to elements in Hochschild homology, but of course this assignment behaves additively in short exact sequences.
So you shouldn't have complained about, not my question about Chebyshev.
Modulo the fact that, again, you are taking all extensions of the Q.
Yeah, that's right.
Yeah.
I see. Well, I still want to maybe it's a longer question, but how do you get those large objects, or those arrows you went back and,
Yeah, let's maybe declare it over. I'll be happy to tell you.
Okay, yeah, so maybe make minutes again and the next stop will be in half an hour or 55 minutes. Okay, the second speaker this morning is Oscar Garcia Prada and speak about Higgs bundles in highly Fourier spaces.
Thank you. Well, I want to thank the organizers and especially Ludmil. I met Ludmil about 30 years ago at the MSRI in Berkeley. At the same time, I met Tony Pantev. And I have to say that our friendship has been my main connection to this country. So I'm very pleased to be here. And I wish great success to the new center. So I'm starting with S being an oriented with compact surface of genus bigger than 1. And we have the fundamental group of the surface. And I would consider GR a real form of a complex semisimple Lie group. I could consider actually a reductive group, but today we will just consider the semisimple situation. And actually GR could be complex. In fact, every complex group, semisimple group in particular, can be regarded as a real form of the double. So G would be a real form of G cross G. So what I'm going to say doesn't refer only to real groups that are non-complex, but also to complex groups, but the emphasis will be on real forms. And so we want to consider representations of the fundamental group of S in GR. So this is simply homomorphisms. And so we want to consider classes, equivalence classes of this objects, but to have a nicer space, we will consider reductive representations. Those are the ones that, if you compose the representation with the adjoint representation, this decomposes in a direct sum of irreducible representations. So I want to consider, the pointer doesn't quite work here, but I can point with my hand. So we consider this set of all reductive representations, and then consider the moduli space of representations of the fundamental groups in GR, or call it sometimes GR character variety of S, defined as the set of equivalence classes of reductive representations modulo conjugation by an element in the real group. And so the character variety is an analytic variety, and if GR is algebraic, then there is an algebraic variety. So there is, one can associate a topological invariant to representation, and one way to do this is by relating representations of the fundamental group in GR to flat GR bundles. And so I will assume in this talk that GR, most of the time, not all the time, but most of the time, the GR is connected. And so, so flat GR bundles are topologically classified by the fundamental group of the group GR, right? And so we can fix this invariant, this topological invariant, and an element in the fundamental group of the real form. And then fixing this invariant, we can consider subvariety RC of the character variety by fixing this topological class, so this fundamental group.
You didn't get Lagrange bundle classified by one of GR, it's always so.
Sorry?
No, he means H2 with coefficients.
Yes, H2 with coefficients in pi 1. So if you want
H2 is coefficients.
yeah, H2 with coefficients in pi 1, but you know, we're on the surface, is isomorphic to pi 1. I avoided the long exact sequences and so on. And there are ways of associating this topological invariant from the representation point of view. But from the flat bundles point of view, you just have the homology set sequence and the coefficients in the invariant X values in H2 with values in I1 of GR and thus isomorphic to I1 of GR, right? So we fix this invariant, we have this variety, and so it's well known that if GR, if this real form is compact or complex, the connected components of the character variety are in bijection with the fundamental group of GR. So this invariant classifies, gives you all the number of connected components if the group is compact or complex. But this is, the situation is very different for non-complex, non-compact real groups. And in general, the map that associates to the component, the invariant, is neither injective nor surjective. And there is a simple example to illustrate this. An important example is the case of SL2R. So here, the fundamental group of SL2R, SL2R retracts to the circle, so the fundamental group is the integers, and so the topological invariant here is the Euler number of the flat bundle, or the representation. And so you can fix this integer and consider the subvariety RT of the character variety for SL2R. And so Milner, in 1958, he proved that RT is empty unless the Euler class in absolute value is bounded by the genus -1. So this is telling you that the map before is not surjective, not every value of the degree can occur. And so you have this bound here on the Euler number. But also, then, about 30 years later, Goldman and Hitching, with different methods, proved that, in fact, if you fix the topological invariant strictly less, the Euler class strictly less than the genus -1, then this is connected. But if you take the value, the maximal value, then this has 2 to the 2G connected components. And so the map is not injective either. So this illustrates exactly the failure, how different this is to the case of a compact or a complex group. And, but more importantly somehow, in relation to my talk, is the fact that the maximal component, the one that has maximal Euler class, positive and negative, can be identified with the Teichmüller space. So this corresponds to Fuchsian representations, and so the discrete and faithful representations of the fundamental group in SL2R, and via the Riemann and Poincaré theorem, we can relate that to hyperbolic structures, and the holonomy gives you the representation. So Goldman in his thesis actually made the comment that this exactly, you can identify this component, maximal component, with the Teichmüller space of the surface. Okay, and so the question that arose, I think, a long time ago, and 30 years ago, is whether there are other simple groups with similar features to those of SL2R. And more precisely, I mean simple groups for which the moduli space has connected components that are not distinguished by the primary topological invariant, the element in pi 1 that I said, and perhaps more significantly, consisting entirely of discrete and faithful representations. Okay, that was a question, a quite natural question. And so over the years, it started actually 30 years ago, at the time that Ludmil and Tony and I met, Nigel Hitching identified a class of groups that split real groups. Later on, another class of groups for which this would happen are non-compact groups. I would call Hermitian groups. What I mean is the symmetric space defined by the group is Hermitian, right? Of tube type, I will explain this. So these were two classes of groups that were identified having this phenomena, and for a while, this okay. Let me explain the first. How the occurrence of these two situations, and I will take a point of view in complex algebraic geometry by using Higgs bundles, right? And let me explain now what is the Higgs bundle. They have already occurred in the previous talk. But so now the surface is endowed with a complex structure. So X is a compact Riemann surface. And I have, as before, my complex semisimple group in a real form. And now I choose a maximal compact subgroup of GR, I call it HR. And this choice gives me a decomposition of the Lie algebra of GR, the Cartan decomposition in the Lie algebra of HR, and the orthogonal part with respect to the Killing form. And so I complexify, so there is the isotropy representation that of the group HR in MR, but I complexify that representation. Let me actually write here, just click in benefit of this, because I'm going to use this notation, it's easy to forget. So yeah, so we have GR, semi-simple real form of this semi-simple complex group, and then we have a maximal compact. Maximal complex group, then we have the Cartan decomposition. And then I will denote by H is the complexification. So H and M are complexification of HR and MR respectively. And another ingredient is this isotropic representation, the complexification of the isotropic representation. Okay, so there, forget. So with these ingredients and the compact Riemann surface, we can define what I will call a GR Higgs bundle on X, and this is a pair where consisting of a holomorphic principal H bundle over X. H is the complexification of HR. And then the Higgs field, phi, is a holomorphic section of the bundle associated to the isotropic representation tensor with the canonical bundle of the Riemann surface, the canonical line bundle, right? So in particular, if the group is actually complex, G, let's say, then this is a G bundle, and this is the adjoint bundle, and so it's more familiar perhaps for all of us. And so let me just quickly give some examples for those who have sort of familiarity with these objects. In the case of, for example, starting with S, L, and C, and the classical groups, we can express these things in terms of vector bundles. So in this situation, the maximal compact, sorry, there is a mistake. This is HR. HR is SUN, and so, and this is H, sorry, all these typos, different notations used at different times. So this is SL and C. And then an SL and C Higgs bundle is equivalent to a pair consisting of a holomorphic vector bundle. Because we are working with SL and C, the determinant is trivial. And then we have this Higgs field, which is a twisted endomorphism of the vector bundle twisted with K with a trace equal to 0. And with these objects, there are notions of stability and semi-stability and polystability and so on that you're familiar with these notions for vector bundles is similar. And these are the objects that were introduced in the original paper by Hitching in '87.
I'm very confused about the notation. Which is G and which is GR?
Yeah. I am G is SL and C. I said there is a typos. This is HR, right? This is H, right?
So what is GR?
Yeah.
Sorry?
GR. What is GR?
GR is SL and C itself.
Okay.
I should have used. Yes. I said before that actually sometimes the real group is actually complex, right? So my GR is actually yes. Sorry about that. GR, the group is SL and C. Maximal compact is SUN, right? The complexification is itself, right? And so this is the Lie algebra of SL and C, right? Yeah.
So H and C are the same.
I think you should forget about this. Maybe just here. Okay, forget about that, right? And then in accordance with the previous notation, GR is actually SLNC. If you want to know what was G here, I said before, is a double of SLNC, right? Now, but HR is SUN, right? And then the complexification of HR is, of course, GR, right? So these are just the usual Higgs bundles, the vector Higgs bundles.
The G is the double.
G is a double, yes. So if you want to, G in this story, this was supposed to be the easy example, sorry, is the double, right? So these are the, and so MR, if you want, is, this is just the Lie algebra, it's GR, right? And this is just.
I forgot what was the definition.
Sorry?
So HEC is just SLNC.
Forget. Forget about that page. There is full of typos, right? So this is my example, right? And so I can think of, if I take this definition, right, I can think in vector bundle terms. And so the objects are just a vector bundle. E is a vector bundle, rank n vector bundle, holomorphic, with determinant just trivial, right? And the Higgs field is just like in the previous talk, actually, but Denise was just, a twisted endomorphism that trace mostly equals 0. Right? So these are the familiar objects introduced by hitching the still passive. Right?
Does it mean N? Is it NC, which is supposed to be SLNC? I agree, GR is SLNC, but M.
MI. It's SUN.
No, sorry. This is.
The algebra.
You are just confusing me. Let's say that if you take, let's put it this way. Okay, if you take as the real form the complex group itself, which is the real form of the double, then a Higgs bundle, right, according to this definition, or just will be a G bundle, right, and the Higgs field will take values in the adjoint bundle.
I don't disbelieve that statement. I'm just trying to understand the notation.
Well,
I think you get also type on your handwriting here. It's not a SLNC, not a SLNC, then you get MR, GR.
No, this is the group, my group is SLNC,
Yeah.
so the Lie algebra is the Lie algebra of SLNC.
Yes, but what about M?
So M is actually,
It's
yeah.
Hermitian matrices.
No, but sorry, I am confused here.
Yeah, G is anti-Hermitian matrices and the Hermitian matrices.
Right.
Yeah, MC, yes.
Yes. Okay, sorry. So I just wanted to remind you the notions of stability and so on. That is the usual vector bundle sort of condition, right? And perhaps so these are the original objects introduced by Nigel Hitching. Actually, I wanted to give. I hope there are no typos here. Another example that is a real group, right? A real group that is not complex. This is a symplectic group, sp2nr. So maximal compact is UN, right? The complexification H is GLNC, and this complexified isotropic representation is actually S2 of Cn by S2 of the dual, right? So a sp2nr Higgs bundle is equivalent to a triple in this situation, consisting of a rank n holomorphic vector bundle and two Higgs fields that are actually here and symmetric, right? And just to make the point that stability in this situation is a bit more involved than just in the previous case, and you have to check some numerical condition on, in particular here, two-step filtration, not just subbundles. And so my point, so this is an example that I will revisit in a few minutes, is that in general, there are appropriate notions of stability and semi-stability and so on, and we can consider the moduli space of polystable GR Higgs bundles as a set of isomorphism classes of polystable GR Higgs bundles. And so these spaces have been constructed in different methods in the context of complex algebra geometry, using GIT and so on, Mitsude, Simpson, Schmidt, and etc.
So there is some like uniform definition of stability.
That's right. There is a uniform definition of stability, and in the two examples that I said, it can be expressed in terms of subbundles in one case or twisted filtration in the other case. Whenever you are working with classical groups, it's always expressed in terms of filtrations. There's an abstract general notion of stability and the construction of the moduli spaces. So that notion of stability actually emerges very naturally if you want to construct this from the point of view of GIT, for example, like Mitsude and Schmidt, to use geometric invariant theory. But it also emerges when you want to solve a gauge-theoretic equation for a GR Higgs bundle. And this is the Hitching equation. This is an equation for a reduction of a structure group of GR to the maximal compact, what we can call a metric. Right? That's when the group is GLNC or SLNC, this is really a Hermitian metric on the vector bundle. And so this equation involves the curvature of the Chern connection compatible with the metric and holomorphic structure. And here you have a conjugation that given by the real form and combining that with the conjugation of one forms. And so you have this equation here. And the theorem is that the stability, polystability of this object is actually equivalent to the existence of a solution to these equations. And this is proved in the original paper of Hitching for SL2C, group SL2C, and then Simpson for general complex groups, and then later on with my collaborators, Radon and Goten for general real groups. So the main thing here is there is the non-abelian Hodge correspondence that establishes a homeomorphism. So if you have your smooth compact surface S at the beginning, you choose any complex structure in S, and then you have the Riemann surface X as J, then there is a homeomorphism between the moduli space of representations, the character variety, and the moduli space of Higgs bundles on the Riemann surface. And one ingredient in the proof is the previous theorem of existence of solutions to Hitching equations, and there is another PDE theorem that you have to solve. And this, out of the solution to the Hitching equations, you can actually construct a flat connection, GR connection, and whose holonomy is reductive, that goes in one direction. And the converse is a theorem of Donaldson in the case of SL2C and Corlett in general about the existence of twisted harmonic metrics, twisted harmonic reductions of a structure group on a flat GR bundle whose holonomy representation is reductive. Right? So these are the two. Okay, so this is the non-abelian Hodge correspondence, and this is the tool that we will use to actually tackle our problem, right? And so, and this is, but let me say first that also in the context of the Higgs bundles, there is a topological invariant, and again, you know, this is a topological class of the H bundle, and similarly as before, this is given by H2 of the surface with values in the fundamental group of H, but because HR is also a maximal compact of H, so H retracts in HR, so the fundamental group, actually the fundamental group of GR, H, and HR are the same, right? And so you have this invariant, and you can fix it to consider the subvariety MC with this fixed invariant, and the non-abelian Hodge correspondence restricts, of course, to give a homomorphism between the character variety and the moduli space of Higgs bundles with this topological invariant fixed. Okay, so let's now get to this. I said there are two families of groups that were identified where similar phenomena to the case of the tabular component arise. And so the first class was the split real forms. So GR split real form. So this simply means that in the Cartan decomposition in MR, this contains a maximal abelian subalgebra of GR. And for the classical groups, these are SLNR for SLNC, the symplectic group that we have seen, and then SONN or SONN plus 1 for the classical groups. And of course, every semi-simple complex group has a split real form. And so let's consider the case of SLNR, right? And so GR is SLNR, but actually we will consider the invariant polynomials of SLNC, and we have the characteristic polynomial of an element is SLNC, and this allows the definition of the Hitching map. The Hitching map, the moduli space of Higgs bundles for SLNC, by evaluating these polynomials in the Higgs field, and we obtain an element in this direct sum of sections of these differentials, right? The Hitching map is, and the Hitching fibration is a very important subject. It is not, the emphasis here is not on the Hitching fibration, but actually on the fact that there is a section to this map. Hitching constructed a section of this map, so a map from here to the moduli space, and actually showed that this is a connected component of the moduli space for the SLNR Higgs bundles. You can realize that the SLNR Higgs bundles somehow sit inside here, and so this section hits the character variety for SLNR, and in fact, it defines a connected component that is now referred as Hitching component. So, in the case of SL2R, this Hitching component actually coincides with the Teichmüller space identified with quadratic differentials. Right? So, this H0 of k squared, that's what we get in the case of SL2R. And so Hitching gave a construction of using a constant section of this, give a section of this vibration for general split real form, and the Hitching component is essentially unique if GR is a split form of a joint type. For example, in the case of SL2R, remember we saw that there were 2 to the 2G components. All of them get identified when we go to PSL2R, and this is a familiar technical space. And now every representation in the Hitching component can actually be deformed to a representation that factors through the Fuchsian representation of pi1 of S in SL2R, and so that is that this one is in the Teichmüller space, and so this SL2R here is actually the principal representation that every split real group has, right? So Laborie, later on, this is another fundamental aspect of this theory, he introduced a concept of a Nosov representation, for representations of the founded group, and I will mention some of this later on. And the Nosov representations have many interesting geometric and dynamical properties, and in particular, the Nosov representations are discrete and faithful. And so Laborie proved that a Hitching component consists entirely of Nosov representations, and hence discrete and faithful. So that was one class of groups that the split real forms. Let me now get to the groups of Hermitian type, meaning that the symmetric space, GR mod, the maximal compact, I said I was going to remind you this notation, maximal compact, is Kähler.
So, just before you come to testing, so can you, maybe you probably said it, but what is the correspondence then of this component, these 2G components in this Hitching?
Yes, what I so in the previous in the case of SL2R, yes, we saw that the maximal Euler class, there were 2 to the 2G components.
Yes.
Right?
Yes.
What I am saying that if you take the adjunct group PSL2R, then all of those components get identified somehow. What I will do, please SL2R, they are all isomorphic, right? There's only one component. And this is in accordance to this statement that in the case of a group of that joint type, the Hitching component is essentially one. Okay? Right. Because maybe you were puzzled when I previously spoke about SL2R, there are all these copies of the tachymetric space. There were all these copies because we were dealing with SL2R. If you deal with PSL2R, you only have one component. Right? Okay, now let's get to the Hermitian type. And actually, it's interesting because SL2R is split on the one hand, but it's also Hermitian. Since the symmetric space is, of course, the hyperbolic plane. And so it belongs to both families, right? And, but the classical connected simple groups of Hermitian type are SUPQ, the symplectic group that we just saw, and then the non-compact dual of SO2n, and this real form SO2n. I take this because I want the connected component. And then there are two exceptional real forms, one for E6 and another one for E7. Right? So this is very familiar.
Can I have a very basic question?
So
I have a very basic question. So, non-abelian Hodge correspondence on the character variety side, I wanted to identify the real connections that we have fixed locus of anti-holomorphic involution. In particular, I wouldn't expect them to carry a complex structure.
okay, you can actually see this moduli. Okay, the moduli space of Higgs bundles for the real group GR actually do appear at the Higgs bundle side of the complex group from a holomorphic involution, right? And that corresponds to that anti-holomorphic involution at the side of the character variety.
I can explain that. So it's non-abelian Hodge correspondence takes that anti-holomorphic involution to a holomorphic.
That's right, a holomorphic involution. There's a holomorphic involution at the Higgs bundle side converts into the, Poincaré knew this already because of the way of he thought of real forms, but of a complex group as real anti-holomorphic involutions, right? And he showed that actually the equivalence classes of those are in correspondence with equivalence classes of holomorphic involutions, right? And via this relation of Gartin, we can show in the Higgs bundle situation that is what happens. That's how actually the Higgs bundles for real groups show up inside the moduli space. Right? And that applies for any real form, not just a split one, for all real forms. Any other question? Okay, so let's get to these other families, so these groups of Hermitian type. And so if GR is simple, then the torsion-free part of the fundamental group is actually isomorphic to Z. Then the topological invariant in this situation is, as in the case of SL2R, is an integer. And this is referred as a Toledo invariant in this context. And so there is an inequality that generalizes Milnor inequality in the case of SL2R. And this says that the Toledo invariant is bounded in absolute value by the rank of the symmetric space times the genus -1, right? So this inequality, from the point of view of Higgs, for classical groups, had been proved in the case of the symplectic group by Turayev and by Domich Toledo, and using Higgs bundles in my work with my collaborators, Peter Cotton and Steve Bratlow, and general proof for representations by Berger, Yossi, Winhardt, and also using Higgs bundles without using any classification in my work with Picard and Rubio.
So the proof of what?
Of the Milnor-Wood inequality.
Of the inequality.
This inequality.
Yes.
This inequality, actually, from the point of view of Higgs bundles, is a consequence of semi-stability applied to some particular subobject. Right. So again, the attention here, as in the case of SL2R, is in the maximal case, when this Toledo invariant is maximal. So that is the rank of the symmetric space times G-1. And so let me consider the case first of the symplectic group that I mentioned before. The symplectic group is a fantastic group in this story because it's both split and Hermitian. It's about the only group that has that property, except some low-rank isomorphisms. And so remember that as I explained before, an sp2nr Higgs bundle consisted of a holomorphic vector bundle of rank n, and then the Higgs field had actually two pieces. These two pieces were symmetric homomorphism from the dual of V to V tensor K, and from V to the dual of V tensor K. And so is the power of using Higgs bundles in proving the Milnor-Wood inequality is actually that there is a more refined inequality that the Milnor-Wood that I wrote and that one finds with other methods. And this refined inequality involves actually the ranks of the Higgs fields beta and gamma in this way. And again, as I said, this inequality is obtained by means of semi-stability. And so this gives you the Milnor-Wood inequality that I wrote before. But this inequality here is very important because, in particular, it tells us that if we assume that D is maximal, for example, positive, the same for negative, that is, in this case, n times g minus 1, the rank of the symmetric space is n in this situation, then one actually deduces that gamma is an isomorphism. This gamma here is actually an isomorphism of vector bundles, just for topological reasons.
What would bring you rank point-wise at any point?
This is the rank of beta and the rank of gamma.
What does mean? It's kind of metrics.
These are matrices. These are matrices.
Depending on parameters on the point on the curve. It's every point on the curve.
Yeah, that's right. Yes, but point-wise, you
Point
just care. It's just
point-wise.
Actually, in general, there would be something like this, and one can make sense of that, what that means in general, right? But in this particular case, it's is the usual sort of rank. And so then,
Could I persuade you to take 2 steps back?
you mean because you are not seeing what I'm? Oh, I'm sorry. Let's see if I can. It's not to see that I don't have a good sight. But anyway, I'll try and complain again if I do it. So the fact that gamma is an isomorphism, right? If you go back to gamma there, it makes you think that it has an orthogonal structure. It's a K orthogonal structure. But if you choose a square root of the canonical bundle, and you define a new bundle, W, which is V tensor L, then you can endow W of a symmetric, of an orthogonal structure. That's one thing. Gamma is basically that, once you choose the square root of the canonical bundle. And then you can recast the other Higgs field beta in terms of this gamma, right, this theta thing. And at the end of the day, you actually obtain here like a Higgs bundle, but actually the twisting is not by K, it's twisted by K squared. The definition that I gave of a Higgs bundle applies for any twisting. But here appears twisted by K squared, and the group now here is GL and R, whose maximal compact is of course the orthogonal O and R, and the complexification is this group O and C, right? So this is the result, that there is an isomorphism of complex algebraic varieties that identifies the maximal Toledo moduli space with another moduli space of Higgs bundle kind of objects, where now the twisting by K squared. And one of the important things of this correspondence here is that actually it detects new invariants. So having fixed the Toledo invariant that was maximal in this particular case, now we can detect other invariants that are given by Stiefel-Whitney classes of objects here, given by the orthogonal bundle. Right? So that's one of the things. So what is the story in general? Now, in general, and you need a situation where the group of Hermitian type is of tube type. What this means, this can be expressed in several ways, but in terms of the Shilov boundary, which is a part of the, if you look at the Hermitian symmetric space as a bounded symmetric domain, right? There is the topological boundary, and the Shilov boundary is just one part of the boundary. It's the only close GR orbit. And so if that Shield boundary is a symmetric space, in general it's a homogeneous space. If it is a symmetric space, compact symmetric space, then you do have this correspondence here, right? And you have it when this is the definition of tube type. The tube refers to the fact that the bounded symmetric domain can be seen to be biholomorphic to a tube over a cone, and or in other words, it has like if you think of the Poincaré disk as being biholomorphic to the upper half plane, this kind. So these are symmetric spaces that have similar realization to the upper half plane. That's sort of a tube kind of thing, right? And so for those groups, then we have this general correspondence that we call Cayley correspondence, precisely because of the relation somehow between the Poincaré disk and the upper half plane. There are other reasons to call it Cayley correspondence, but that's one. That identified the maximal Toledo invariant moduli space with this K squared twisted for another group. And this group here is related to the Shield boundary by the fact that this here, so I will now go, this here is the dual, the non-compact dual of the Shield boundary. And so this identifies the group there. In the case of the symplectic group, sp2nr, this was SLNR, GLNR, excuse me. Okay, so this was proved for the classical groups in a one-by-one case over the years with Steve Bradwell and Peter Goten, and then the general non-classification proof was given with Olivier Picard and Roberto. So like in the case of Hitching components, Berger, Yossi, Labrie, and Winhard proved that this consists entirely of Anosov representations, and so then they are discrete and faithful, and something that I didn't mention before but also happens in this case is the mapping class group of the surface acts properly on these components. And so here's a question that let me check the time. So the question is, are there other groups besides split and Hermitian real forms of tube type for which special components exist in the sense that I said before? Yeah? So that consists entirely of discrete and faithful representations, and they are not distinguished by the primary topological invariants. For a long while, it was believed that these were the only two classes for which this phenomena happened. And, but then it turns out we found another family of groups, SOPQ, and this was originated in the thesis of one of my students, Marta Aparicio. Yeah. And I gave this problem to her, sort of to compute the number of components, hoping that the usual invariants will count components using the Morse theoretic techniques that Hitching has used and we have used in this kind of problems. And she was quite discouraged because in this Morse theoretic thing, you analyze some critical subvarieties and some minima, and there were more minima than one expected. So this wanted to know whether this consisted entirely of polystable things or what. And so she abandoned mathematics. She went into insurance company. But we took actually the problem some years later and found that indeed the Morse theoretic computations that Marta had done were an evidence of other components. And in fact, there were, once you fix one of these topological invariants for SOPQ, there is a component, but then there are other components. And these other components that in this work we constructed appear as some sort of generalized Cayley correspondence, as I explained before. And these components can be identified with now another moduli space for another group, SO1, q minus p plus 1 with a twisted by kp. And then something, this differentials here. So it's a sort of a mixed situation of the split case where you only have this kind of thing, and the Hermitian tube case where you only have this kind of thing. So this was quite a surprise. But then simultaneously, Guichard and Dinhard had been working off a notion of positivity for real groups, and it was some evidence from their side that SOPQ was indeed a good candidate. And so a combination of results, recent results by Guichard and Dinhard, and this correspondence showed that these components actually again consist entirely of discrete and faithful representations. I will come back to this in a minute. And so the main goal of the rest of the talk, which is not much, is to give a full classification of all the Lie groups for which you have real groups for which there is this phenomenon, right? And I will give a general construction and classifies these groups and gives a general Higgs bundle parameterization, right? And so this is joint work with Stephen Bradlow, Brian Collier, and Peter Cotton, and Andrea Oliveira. And the key thing to do this is the use of SL2 triples and important elements and so on. So let me explain. Now you have G to be the Lie algebra of the group, semi-simple complex group. And remember that, recall that an nilpotent element, an element of G is nilpotent if the atophy is an nilpotent endomorphism. And so we have the nilpotent cond, and the group G acts on N by conjugation with finally many orbits. And there is an important the open dense orbit consisting of the principal orbit, right? And so there is a relation between nilpotent elements and classes of nilpotent elements and SL2 triples. You can, once you give me a nilpotent element, you can complete it to a triple, SL2 triple, FHE, so satisfying the Lie algebraic relations of SL2, right? And so there is an equivalence between conjugacy classes of nilpotent elements and conjugacy classes of SL2 triples. So once you give me a nilpotent element in the Lie algebra, G, and I complete it to an SL2 triple, I have two different decompositions of the Lie algebra. So one decomposition is as SL2C module, right? So I can decompose just my Lie algebra under the action of SL2C in irreducible representations and copies of irreducible representations. This is this in here. And then I have another decomposition of the Lie algebra by the eigenvalues, the eigenspaces of the element H, yeah, in the triple, right, this G Yates right here, and the operating by E by the adjoint action moves me Gj to Gj plus 2, and the operating with F to Gj G minus 2. Right? So these two decompositions that I have, once I have this SL2 triple, I can sort of combine them, and I can consider the intersection of Wj with Gj, and this is actually the highest weight subspace, and so I can express the whole Lie algebra as a direct sum of, in terms of the highest weight subspaces and actions of F, right? And so once I have this decomposition, then I can define an involution in a vector space involution in G, right? By this expression here, in V0 is the identity, and in here, in these other pieces, I have this. This is an involution of the vector space. And so here is something special. We call it magical. I don't like this name, but this is what we came up with. We say that the nilpotent is magical if this vector space involution is a Lie algebra involution. And so once you have this Lie algebra involution of the semi-simple complex Lie algebra G, using the relation that I said of Cartan before, choosing you have a real form, right? In holomorphic involutions of the Lie algebra, you can find an anti-linear involution of the Lie algebra, that compact that commutes with this. Cartan tells us that we can do that, and that the combination of both gives me an anti-linear involution of the Lie algebra. That is a real form. So magical triples define me real forms, right? And so here is a classification of the groups for which real magical SL2 triples occur. And not surprising, I mean, these are the magical triple, the real forms that appear from magical triples. Not surprisingly, we have the split real forms, we have the Hermitian of tube type, we have the SOPQ, but the important thing is also we have other groups, and these are groups that are real forms of E6, E7, E8, and F4, and these are real forms characterized by the fact that the symmetric space defined by them is quaternionic, right? This coincides actually with the classification of groups where is this positive structure that I alluded to, like Sharon and Winhard. If I have time, I hope to say something about that. And so the two they're different classifications, but they give the same real forms. Now, from the magical triple, there is a lot of structure there. One can extract some additional information, and this additional information that we call Cayley data are some integers here, M1. There is a distinguished one, MC, then Mn, and then a real form of the G0. G0, remember that the Lie algebra decomposed in eigenspaces of the action of the H in the SL2 triple, and so this is the G0s. So there is a real form also of this G0, and so here is the thing.
G0 is the Cartan, right?
Sorry?
G0 is the Cartan.
G0 is the Cartan, yes. Exactly. And so this is, so Phi is a magical nilpotent with corresponding canonical real form GR, and if GR is a Lie group with such a Lie algebra, then the result is there exists a union of connected components of the moduli space of GR Higgs bundles. We denote this union of connected components by this, actually, they're not determined by just the nilpotent. They only depend on the conjugacy class of the nilpotent, right? And the thing is, the Higgs bundles there have nowhere vanishing Higgs field. So there are no representations which factor through a maximal compact, right? And this union of connected components actually is can be identified with a moduli space of Higgs bundles for this real form of G0, right? Twisted by this, remember there was this important integer here, by this power, and then some differentials, holomorphic differentials. So this is the thing, and this is, and now there's another typo. I noticed this GC is the G0. It's sometimes called the Cayley partner, and so we call this Z, but this is the G0. And so we can find this by defining a map from this space here to the moduli space of Higgs bundle, and is an isomorphism onto its image, which is open and close, and so defines connected components. I have no time to give details about how we define this map. And so these topological components of this image we call Cayley components, and this map here recovers the Cayley correspondence for Hermitian groups of tube type that I mentioned. It recovers also the one for SOPQ, and to me it was kind of not surprised, but a different way of thinking, that actually the hitching section is actually an example of this as well. So the hitching section is a particular case of a Cayley correspondence, where in fact this group here is actually R plus. And so we have just quadratic differentials, and then the quadratic differentials add to the other differentials to recover the familiar Hitchin base. Right? So, yeah. So let me say something about this notion of positivity, right? And why these components, I mean, we identify these components in the moduli space of Higgs bundles for these groups. We have classification of these groups. But why is it that from the non-abelian Hodge correspondence, all the representations there are discrete and faithful, right? So this is, okay, for the split case is known, for, as I mentioned before, Lagrange, and then for Hermitian groups of tube type as well, but in general, why is that true? So this is a notion of positivity that has been somehow introduced, generalized by Guichard and Winhard on some real groups. This involves a parabolic subgroup of the real group, parabolic P. And so this positivity structure in particular gives, I cannot get in any detail, but is the system of a positive semigroup in the unipotent radical, and this allows to define a notion of positive triples in the Flach variety. So you have the generalized Flach variety, and so this gives you a notion of positivity for triples there, right? And so this notion of positivity was built up from this generalizes Lustig total positivity for split real forms, and also another notion of positivity that was available using the Maslov index for Hermitian groups of tube type. And in particular, for SL2R, and where the Flach variety is the circle, a triple is positive if it consists of pairwise distinct points. So with this ingredients in hand, you can define, when you have a group, GR and a parabolic subgroup with a P positive structure, what is a representation, when a representation of the fundamental group of S and GR is said to be P positive. And this is if you have a raw equivariant map from the boundary at infinity of the fundamental group. This is the boundary of the Poincaré disk if you want it, right? Into the Flach variety, GRP, sending positive triples of the circle to positive triples in the Flach variety. So this is what positivity does for you, allows you, and you have to go to the boundary map defined to the boundary map defined to the representation, right? And so, in a recent paper last summer, a year ago, Guichard, Winhard proved the following: that if GR is a semi-simple group having a P positive structure, and you have a P positive representation, then the representation is anosov in the sense of Lagrange, so in particular is discrete and faithful. And well, this was known already before the theorem there, that the set of P positive representations is open in the character variety, but was not known, and this was the important thing, is that the set of P positive representations is closed. But ideally, they want to prove that it was closed in the character variety, but they could only show that it's closed in a subspace of the character variety consisting of representations that do not factor through a parabolic subgroup of GR. And it turns out that actually, in our paper, we proved that the Higgs bundles that were here in these components that I defined before, the scalar components, in fact, there is a subset of positive representations given by the, you can embed the tabular space there. And so there is an open subset of positive representations there because of openness of positivity. And we showed that the representations there do not factor through a parabolic of subgroup of GR. So from our results, we combining our results, previous results, this generalized Cayley construction with this with the theorem of Guichard, Labrie, and Binghard, we prove that the Cayley components consist entirely of positive representations. So they are discrete and faithful. And as I said, the original conjecture was that the set of positive representations was closed in the character variety, full stop. And then, so with only this, with the, oh, something happened, yeah. But this, for the case of SOPQ, for the case of PUPQ, have been used by Bayer and Pozzetti, and using color lemmas. And so for that, so for split groups, for Hermitian groups of tube type, and for PUPQ, SOPQ, then we can just conclude that the Cayley components are the only ones that consist of positive representations, so they are higher technical components. Now, it looks like this color procedure for PUPQ by Pozzetti can be generalized to these other real forms, the quaternionic real forms. And so I have been told by Beatrice Pozzetti that that is the case. And so then this conclusion is that the Cayley components that we construct are exactly the only higher technical components, the only ones that can be discrete, faithful, and the groups that identify they are the only groups for which this phenomenon can happen.
Actually, I have a question. When you're talking about all these closed surfaces, but what about from closed surface with punctures and fixed something?
So thank you for asking that question, because that has been keeping me busy in the last few months. And first of all, okay, so what is that we are doing here? First we have the non-abelian Hodge correspondence. And from the non-abelian Hodge correspondence we do something else, which is this Cayley correspondence, right? So the non-abelian Hodge correspondence for surfaces with punctures in the case of GL and C was done by Simpson, right? Long time ago, in 1990. So there is a general correspondence for any group, any real group or complex that has appeared more recently is my work with Olivier Vicard and Ignacy Mundet. So non-abelian Hodge correspondence is there, right? So you can take this the Higgs bundle approach to the problem. Now the thing is, if you come now to this, let me actually go here. This is the Cayley correspondence, and then you can ask, do we have this Cayley correspondence? What is actually higher? What are higher tabular spaces in the puncture situation, right? So if you think of parabolic, so the language here is the Higgs bundle object is parabolic Higgs bundles, of course. If you look at here, the parabolic Higgs bundles that involve weights and residues of the Higgs field, and here the weights of the parabolic structure. So these are elements in a Weil alcove related to this group, and this is a much larger alcove to the alcove of this other group. So you see, this don't match, right? So there must be something, and so it so happens that actually there is a notion of positivity for a punctured surface that in particular implies that the map from the boundary of the fundamental group, so there are the points corresponding to the punctures, these things must go to the holonomy has to be actually conjugate to must go to G mod P, to GR mod P, right? And so that restriction, that condition there that comes naturally from what one means by positivity in this context, tells you immediately that the weights of the parabolic structure that you have to put here must come from the parabolic structure of here.
Special.
That's right. So some restriction, some special restriction. There are many, you may have your favorite ways of defining higher tabular spaces in the puncture situation, but this positivity condition dictates somehow what are the conjugacy classes that should be allowed.
So also, I don't know, I'm familiar with Simon Philippe.
I have heard there is something related to this, but I have not
okay.
looked, so maybe you can
continue. Because exactly, I think here it has CP1 minus 3 points, so as before.
Yes. Yeah, there are several people that have considered this puncture situation in the context of higher tabular, but there is no systematic approach to this, and somehow this, by using the non-abelian Hodge correspondence in that, and this Cayley correspondence, more or less tells you actually what should be the theory.
Okay. Questions? Thanks, speaker again.
There's certain
Tony, you're the host.
I'm the host.
You're the host.
Okay. All right. It's time. Okay. Well, it's a great pleasure to get on John Ock, who is going to tell us about contact reduction in thermodynamics.
Okay. I'm very happy to be here for this ICMS inaugural workshop. I hope a big success for this institute. Okay, so I'd like to talk about some relationship between contact geometry and thermodynamics. So this is going to be the overview of my talk. So I'm going to first say my motivation for this research and set the stage for the talk. Probably not all of you are familiar with the contact geometry. And then I'm going to talk about the known common practice in the geometric framework of thermodynamics in the contact geometry point of view. And then I'll talk about some contact version of a simplex Weinstein, Marsden-Weinstein reduction in contact geometry. And then I'll talk about how we can apply this contact reduction to derive the statistical, reduce the statistical mechanics to thermodynamic basis. That's the way. So, okay, so let me start talking about the motivations. Okay, so contact manifold is other dimensional manifold, which is commonly called the sister of symplectic manifold. And the contact structure is some hyperdistribution field, the tangent bundle, that satisfies certain non-degenerate conditions. Okay. And a vector field, X is called contact, if its flow preserves this contact structure. Okay. And when this contact structure is co-oriented, it can be written as the kernel of some one form. And that one form is called the contact form. So when you're given contact form, you can talk of, it provides very natural dynamics on contact manifold. And that dynamics can be perturbed to the so-called Hamiltonian, contact Hamiltonian dynamics. It's very similar to symplectic dynamics. The only difference is that in symplectic Hamiltonian dynamics, the constant function provides no dynamics. But in contact geometry, constant function provides the so-called Rev dynamics. So in contact Hamiltonian dynamics, there is a very natural background dynamics going on once you fix the contact form. That's a big difference between symplectic Hamiltonian dynamics and contact Hamiltonian dynamics. And it is easy, actually, in contact geometry, it is much easier to define what Hamiltonian of the associated contact vector field. All you have to do is just evaluate the vector field by the given contact form. But in symplectic geometry, the definition of contact, definition of Hamiltonian vector field is a little bit harder to define. It has to solve some algebraic equation. But in contact geometry, it's very easy. And in symplectic geometries, there is a crucial geometric object, so-called Lagrangian submanifold. And the importance of the Lagrangian submanifold is so high, the Alan Weinstein even declared that everything is a Lagrangian submanifold in symplectic geometry. And actually, there is some other dimension analog of this Lagrangian submanifold in contact manifold, so-called Legendrian submanifold. And the difference between Lagrangian and Legendrian is, the Lagrangian submanifold is exactly half dimension, half of the ambient dimension of ambient symplectic manifold. So there is a natural intersection theory between Lagrangian submanifold. And this is the core of the symplectic topology. And this thing is called Lagrangian intersection theory. On the other hand, the Legendrian submanifold is the dimension is a little bit too small. It's if the contact manifold is dimension 2n plus 1, Legendrian submanifold is dimension n. So generic pair of Legendrian submanifold do not intersect. However, as I said, there is a very natural background dynamics in contact geometry, this Rev dynamics. So, unlikely in symplectic geometry, what's important, what's significant in contact geometry is the entanglement of this Legendrian pair. Or more generally, you look at the Legendrian link, and the interesting dynamic and geometric phenomena one has to understand is how these links are entangled under this background dynamics. So a central question in contact topology, okay. And so how do they, what measures this entanglement of this different component of the Legendrian link? This is the whether there exists some code between two different, or even the self code connecting this Legendrian component through this Hamiltonian trajectory by Rev dynamics. So that's called a Rev code. So a central question in contact topology and in contact Hamiltonian dynamics is to understand this entanglement structure of the Legendrian links relative to the Rev dynamics, or more generally, to a contact Hamiltonian dynamics of a given contact Hamiltonian. Rev dynamics corresponds to the constant function -1 in my convention. So here. And of course, there is some topological question, but in the dynamical point of view, it is also very important to understand some kind of geometric quantities invariant. So one of the crucial invariant, dynamical invariant, is so-called action. when you choose the contact form, you can evaluate this one form along any given smooth trajectory. In particular, we can associate the action integral of this contact form against the Rev core. This collection of those numbers are called spectrum of this contact form, which I denote the spec of n lambda. This is called action spectrum. And if the manifold M and I'm talking about closed. I'm talking about right now closed loop. Okay, I haven't talked about this Lagrange code yet. So I'm here. The action spectrum is the collection of actions for closed loop, and here closed. So the totality of these actions of closed Rev orbit is called the spectrum of this contact form. And because this Rev core satisfies this ordinary differential equation, so there is the infimum. If M is compact, the smallest action is bounded away from 0. That number I denote as T of n lambda. This I call periodic gap of this action spectrum. And one distinguished conjecture in contact dynamics is whether there exists a closed Rev orbit for any given contact form. This is called Weinstein conjecture. And this conjecture has been solved only in 3 dimensions by Taus and machinery of Cyber-Witten theory and so on. But in general, it's widely open.
So how do you define this number if there is no orbit? If there is no closed orbit?
Then it's nothing. So the existence of this closed Rev orbit implies non-triviality of this definition.
Oh.
If there's nothing. You don't, this talking about action spectrum for closed Rev orbit doesn't do much. However, now you can also look at the open string version of it. So now let's suppose you're given Lagrangian link R, let's say compact, and then you do the same game. So you between any Rev code, you evaluate the actions, you collect them all. I will call this lambda this relative action spectrum for this Lagrangian link. And similarly, if M is compact, if R is compact, there's a small list, infimum of these actions, which I call the lambda code period gap. Of course, this when you're given the Lagrangian link, and this lambda code period gap could be smaller and bigger than period gap of closed Rev orbit. So I just take the minimum of them. And this is one of the crucial geometric dynamical invariant of contact dynamics. Okay, so how do we investigate? Let's say, as I said, one of the main things to understand the contact topology and contact Hamiltonian dynamics, to understand this structure of Rev code, right? Or entanglement structure of this Rev code against the given Lagrangian link. How they prove such things. So I'm going to introduce some technical or the analytical tool to investigate such a thing. Just like the Gromov pseudo-holographic curve is the probe of symplectic topologies. So for this, I needed to introduce some background geometric structures. So suppose you are given contact form lambda, and we are going to look at some endomorphism J on the tangent bundle. This is some CR analog of almost complex structure. So this is almost complex structure in the contact distribution. So you can regard J applies to 0 to the Rev vector field. So let me just read it. So for given contact triad, we give it with the contact triad metric. And assume further, we are given a contact Hamiltonian, H. Contact Hamiltonian is just time-dependent functions on this manifold. Now suppose you are given punctured Riemann surface. This Riemann surface could be closed or open with a boundary. And to write down the geometry equation, I also need to choose some one form on the given punctured Riemann surface. And then for given any smooth map, you decompose the differentials into the contact distribution component and the Rev component. I'm writing du pi as the projection of differential to the contact distributions. When you're given this Hamiltonian, you can also look at similar. du is one form. I mean, du is Tm valued one form when you're given u. But I want to also perturb this du by Hamiltonian vector field. Xh is a contact Hamiltonian vector field. So to define Tm valued one form, that's why I chose this one form on this Riemann surface. And that is the perturbed differential. And then using this CR, almost complex structures, we can decompose d pi u as the complex linear, anti-complex linear part. And perturbed contact instant equation is provided this way. The first equation is the component, the governing the contact distribution component. The second equation is very peculiar. This is the equation governing the Rev component. Okay? In particular, if h is 0, and this is du equals 0, and d, okay, maybe I'm going to talk about h equals 0 later. So this is the main equation I'm going to study. It turns out this is an elliptic system, nonlinear elliptic system. So you can define the modular space, and or you can repeat all those things you do for pseudo-elliptic curves or in flow theory in the symplectic manifold. And this equation particularly well suited for the boundary value problem with the Legendre boundary condition. So this is very similar flow theory. In flow theories, there are two closed string version and open string version with the Lagrange boundary condition. So this is exact contact analog of that one. But of course, it's peculiar why there is this exponential factor in front of the equation. And this is the actual beauty of this system.
But excuse me, if you add extra direction to make it symplectic manifold, make it a cone.
Yeah, that's a good question.
Yeah.
But when h equals 0, this is kind of the reduction of the homogeneous version.
Yeah.
But when h is non-zero, this is a purely independent system from that homogeneous Hamiltonian. Those two define completely different elliptic systems. But this one works analytically much better. So I was able to prove this analytical machinery to prove some existence theorem for Rev code between two component link. So you look at the compact Legendre submanifold R, and you move this Legendre submanifold by any contact diffeomorphism psi. You regard this as a two-component link and ask whether there exists closed Rev code connecting these two. This kind of question is central question in if you want to actually establish that what I'm doing is completely non-trivial. So I was able to prove that if the, let's say, C0 norm, this double bar of H is sometimes called oscillation of Hamiltonian. As I said, Hamiltonian is time dependent. What you do is just measure the total oscillation of this Hamiltonian in time. If this one is smaller than that period gap I define, I'm talking about closed case. Suppose the question is right. And then if the period gap is, this Hamiltonian norm, the so-called sometimes half norm or sometimes oscillation is smaller than period gap, there already exists some Rev code connecting these two links. I think maybe I have a chance to talk about this in sunny days, not here. So I'm just saying this for the motivation for what I'm going to do. And so I mentioned that when h equals 0, this equation is much simpler. It reduced to this one. And it turns out this equation is really very close to the pseudo-Lobby curve equation of the simplexization. The only difference is that you just replace the second equation. The second equation says that this U star lambda composed with J is closed. But you replace this by exact. And then you added this primitive as the variable. And this becomes exactly the pseudo-Lobby curve equation, the simplexization. So, okay, so the perturbed contact instanton equation is a flawed Hamiltonian perturbed Cauchy-Riemann equation against the Gromov pseudo-Lobby curves. So the question is, what can you do more with this new nonlinear elliptic system? And one natural avenue is to develop the contact analog to the filtered square categories and do the relevant systematic quantitative study for general Legendre links and investigate their entanglement structures. In symplectic geometry, there is a well-known construction of so-called spectral invariant and so on. So you can try to repeat all these things in this using this equation. But the question is, besides these natural mathematical problems, I want to search for more other core problems to investigate in relation to Hamiltonian dynamics. So this was the motivation for me to look at the thermodynamics. Because in the 70s, the Hermann proposed that contact geometry should be some geometric framework to explain thermodynamics, like the symplectic geometry does for particle dynamics. So let's now go to the next. So let me briefly talk about this particular example of contact manifold. This is one-jet bundle of Rn or R2n plus 1. So geometrically, the contact distribution can be pictured like this. So each plane, this is a three-dimensional picture. So when you follow this Q axis, there is a hyperplane distribution which rotates in some direction. This is the contact geometric visualization of contact structure. You have to remember, visualize in any contact manifold, there is some hyperplane distributions which moves, but in some particular way. Okay, so this is the one way of interpreting the equilibrium thermodynamics in the language of contact geometry. So local thermodynamics is a very strange, actually, physics. It's not completely clear where this thermodynamics occurs. There are some variables, but what this variable really means. So only the local description of thermodynamics is present in physics. So local description of thermodynamic phase space is given by thermodynamic variables. For example, here is the typical example when you look at any book of thermodynamics. So U is free energy, T is temperature, S is entropy, P is pressure, and V is volume. And then the thermodynamic first law can be written as du equal TdS minus PdV. That can be written as this way. And then you can think of the R5 with the contact form given by du minus TdS as PdV. And then thermodynamic first law in equilibrium thermodynamics can be said that thermodynamic equilibrium state is a Lagrangian submanifold. So Lagrangian submanifold represents some kind of equilibrium state in thermodynamics. Okay? And I think maybe motivated by this, Herman made the proposal that I just mentioned. And after Herman made this proposal, there are lots of these articles in mathematical physics which translate given thermodynamics law and phenomena in using contact geometry. But I've found that most of these papers are just translation of the given thermodynamics in the contact geometry language, and so I want to see whether we can do more. So I'm just repeating thermodynamic phase space I call TPS exists only abstractly described through coordinate. And one of the main goals of the present talk is to explain this TPS as a contact manifold by a canonical and covariant reduction process, starting from the so-called kinetic theory phase space, which is projectivized cotangent bundle of space of probability distribution on the statistical phase space, which is nothing but the many-body particle system phase space. And in fact, actually, the Grammerlas asked a similar question. Here is the exact quote of one of his papers. So let me just repeat. Again, the main difficulty on this route. On this route is the meaning how the statistical mechanics is reduced to thermodynamics. Is in the reduction process. The question that arises on both routes, there are two routes he described. Both routes is the following. How shall we make the reduction in order that the essential features of the mechanics put into the original microscopic formulation is kept intact, and the comparability with the thermodynamics of both microscopic and mesoscopic formulation is guaranteed. So one of the main goals of the present talk is to explain this reduction process as a contact reduction in the contact Hamiltonian geometry. The central question is where does this other dimensional lattice come from? So that's one of the main actual issues I want to address.
So this should be like a symplectic reduction, like a...
Yeah, it's a contact version of symplectic reduction, but it's a little bit subtle because contact structure. Yeah. So one of the product example of contact manifold is a projectivized cotangent bundle. So this is the space I'm mostly focused on. And here is the contact structure on this projectivized cotangent bundle. Here the point is that this definition does not require any one form. So that's why I chose this projectivized cotangent bundle over this so-called one-dot bundle. And in fact, this is more relevant for what my purpose. So I'm going to sort of replace n by probability, this space of probability distribution later. Okay, so local description thermodynamic phase spaces goes like this. So you are given some n variables. You may think of this just the position variables in particle mechanics, but there is an additional this W, sometimes called this I think a primitive or something. We are saying n+1 they call extensive variables, where W be thermodynamic potentials. And then you can look at the conjugate variables, add conjugate variable y1 and yn. And then the contact form is dW minus y dx. The thermodynamic TPS is a pair, this T, whatever the space, and then this corner of this eta. Eta is one form. I go down there. So next, one of the of course important object is contact morphisms. So contact morphism is just preserve any diffeomorphism preserving the contact structure. When you're given one form, contact form, that this diffeomorphism may or may not preserve this one form. So when this diffeomorphism preserves this contact form, we will call strict contact morphism. But that's not that interesting. More the general definition is common. General definition, this second one, phi is a contact morphism. The first one, I mean. So in terms of the contact form, that condition is equivalent to the existence of this function g, such that this first condition is equivalent to saying that the pullback is the multiple of this given contact form. So you can just write e to the g as f and g as the logarithm of f. So here is the example I gave you. So here is the W1 is S1, X2, W is U, and X1 is S, and X2 is V, and then it's conjugate variable put this way, and then you get exactly that one form. But in thermodynamics, depending on circumstances, we change the variables. Sometimes apply the Legendre transform and so on. And those transformation doesn't preserve contact form, but it preserves contact structure. So from this simple example, it is quite clear that this contact structure is a more important object of concern than form itself even in thermodynamics. So this is just another example of contact transformations out there. The first example is strict, but the second one is not strict. Okay? So this is just so this kind of transformation, sometimes this is called free energy. I don't remember the kind of name in some. Anyway, the second one is the entropy representation with this free energy representation. Going back and forth involves some non-strict contact morphisms, but the background contact structure doesn't change under this transformation. So postulate thermodynamic postulate one is that any change of thermodynamic representation should be a contact morphism on this TPS. For example, the Legendre transformation is one such here. And the second one is, as I mentioned before, the Legendre submanifold should be the description of equilibrium of thermodynamics. So here is the second postulate. Any thermodynamic system can be represented as a triple. the contact manifold and contact structures together with some Legendre submanifold with some representation given by thermodynamic potentials. So here is a typical Legendre submanifold that appears in thermodynamics very often. Just this graph of one-jet graph of functions, or this projectivized version. So in summary, the thermodynamic representation corresponds to contact morphism. Legendre transformation corresponds to strict contact morphism. Equilibrium state corresponds to Legendre submanifold. Thermodynamic fluctuation involves some other structures, so-called Pero-Sasakian metric structures. And thermodynamic process should be just an example of contact Hamiltonian dynamics. So different thermodynamic systems can be regarded as some dynamical system governed by some different Hamiltonian. Of course, in thermodynamics, the kind of Hamiltonian that appears is very special, just like the Newtonian mechanics. So in Newtonian mechanics, the Hamiltonian is total energy, kinetic energy plus potential energy. That's the way how the Newtonian mechanics went through. And similar things happen in physics, but as a mathematics, so you can consider all possible as Hamiltonian and look for some general property of the. Okay, so this is something that has been known in the geometric, in the effort of understanding thermodynamics using contact geometry. But I'm still puzzled why the thermodynamics should be other dimension. So I want to sort of get this other dimensionality from the very first principle of statistical mechanics. So let me briefly recall the reduction process, symmetry reduction in physics. We know that translational symmetry provides momentum. Angular symmetry provides angular momentum. And this kind of reduction process is greatly generalized by Marsden and Weinstein in symplectic geometry using the so-called moment map. So let me briefly recall. So symplectic moment map goes as follows. M omega is symplectic manifold. Let's say G is a Lie group acting symplectically, so preserving the symplectic form. And then the moment map is a kind of systematic way of organizing the total symmetries of this group action. That is defined in this way. So J psi, sub psi is Hamiltonian of the generating vector field given by this real algebra element psi. And then one of the well-known theorem by Marsden and Weinstein is that if you look at the preimage of regular value of this moment map and take the quotient by isotropic group of this regular value, and the theorem is that this carries symplectic form. It very naturally becomes symplectic manifold. In particular, this quotient is always even dimensional. So, why does this reduction enters in here? In the statistical mechanics point of view, the thermodynamics is the average of mechanics of many-body particle system. But when you take the average, you need some kind of probability distribution. That's how this probability enters in statistical mechanics. So many-body particle space physics, particle space, okay, with any observables, so you look at many-body particle system, and you look at some n observables. Then you make an observations. This process of making observation can be regarded as averaging out all the unnecessary things. And that's the way how the physicists derive thermodynamics out of this statistical mechanics. So I want to regard that reduction process as a contact reduction. Starting from some huge contact manifold and going down to this finite dimensional thermodynamic phase. The question is, what is the huge starting contact manifold? So that's what I'm going to do. But first I need to make precise what the definition of contact reduction is. Because there are various definitions in the literature, but most of them, all of them involves the definition of contact form, not just the contact structure. So the outcome in the literature always depends on the contact form as a reduced contact manifold. But here I want to define the reduced contact manifold depending only on the contact structure, independent of contact form. So that's why. So this strict contact reduction is well known. It's already.
Excuse me. So the notion of moment map is independent of choice of contact form.
Right. It depends on it, but the final outcome will be independent. So contact moment map is very easy to define. As I said, it's much easier to define it in simplex geometry. So all you have to do is, you suppose you're given group action that preserve contact structure.
So we start with a symplectic manifold? We start with a symplectic?
No.
It's written.
Oh, sorry.
It's
Sorry.
written.
No, because in your previous slide, you started with a symplectic manifold.
No, that's a symplectic. Well, anyway, it's a typo. Sorry. This one is symplectic contact manifold, and G legal of acting contact morphically. The contact moment map is when you're given contact form is just the evaluation. You remember this contact Hamiltonian is just evaluation of this contact form against this vector field. So this is just analog that I should have put negatively to be completely consistent. And strict contact reduction is just exactly the same as the simplex reduction, but I want to generalize this to the non-strict case. So let's go back how this so general contact morphism is the pullback is the positive multiple of the given contact form. And if you go back to the definition of contact this moment map, you can see that this moment map is not G equivariant. So what's happening is this is the formula for the defect of equivariance. If the exponential factor is not there, that means it's equivariant, cosine equivariant, as like in symplectic case. But the lemma, this lemma shows that there is conformal factor. So it is natural to everything you look at the productivization of these things. So I look at this projective moment. Yeah, even in Poisson geometry, there has been the definition, the group valued moment map, and all kinds of nonlinear moment map has been used in relation to Poisson geometries. So my attempt of looking at the defining projective moment map can be regarded in that spirit. So instead of looking at the target space, linear space, I want to look at the projective space. For u equals 0, of course the zero regular value is special because if the value is 0, this is suddenly obviously holds. So for non-zero case, so for zero case, we just define the reduced space in the same way. But for the question is when this value invariant is non-zero. So what do we do?
So when G is S1, this is trivial.
When
G is S1, projective moment map is trivial.
no,
PR is 1 point, right? No?
y is 1. A circle is one dimension, right?
Yeah, but projectivization,
It's there are 2 points.
2 points,
It's
I see.
1 point. So 0 and another point.
I see.
So projective moment map is nothing but just the projectivization. You look at the dual of real algebra, you take out the origin, and then you look at the projective. So projective moment map has that projective space as a value, the codomain. And contact reduction is, now here is one subtlety. So in symplectic reduction case, the coordinate isotropic G mu, this is the isotropic group of mu under the coordinate action. So that's the isotropic group you should quotient out. But in this game, that group is not correct. So you should redefine the isotropic group in the following way. So this is the isotropic group of projective moment. So mu is non-zero. So you look at this projective element, and then you look at some maximal Lie algebra contained in the kernel of mu. Anyway, so this is the one crucial difference. And then main theorem with my students is that this quotient carries natural contact structure. So this is the precise contact reduction theorem. And this one doesn't depend on the choice of contact form. Okay, so this is the reductions process I defined. I want to apply now this reduction process to derive thermodynamic phase space as a reduction. Okay, so let's go back to a quick review of statistical mechanics on kinetic theory. So in statistical mechanics, we look at the many-body particle system. That the total phase space cotangent bundle of R3n if you're given capital N particles, and that has natural symplectic form, direct sum symplectic form. But here I want to emphasize this space also has natural measure associated Liouville measure or R3n, and this is after all is the isomorphic to the Euclidean space, so you can also look at the Lebesgue measure. In this case, Lebesgue measure and Liouville measure coincide. So I want to look at this triple as the phase space, statistical phase space. I will call SPS. And then I mentioned this reduction involves the averaging process. So it depends on what kind of probability distribution you're going to use. And that's how this probability enters in this game. And I will call the space of probability, and then you look at the cotangent bundle and then projectivize to look at the natural contact form. So that's the space, the contact manifold. The starting contact manifold is projectivized cotangent bundle of space of probability distribution on this many-body particle system. And then observables is nothing but just a function, a collection of functions. You may call this, if you're given probability densities, you can think of this as random variables. So just collection of n functions. We call a system of observables. And the observation is just the averaging of these observables. But there is one very particular observable which doesn't involve any choice. Because we are looking at this probability, and then we all have a very natural background measure, Lebesgue measure. So you can define so-called relative entropy. And this is, I mean, sometimes von Neumann or the Gibbs entropy is the function naturally defined on the space of probability. And by definition, probability distribution has a constraint. The integral is 1. So this, in that sense, this observable is a very particular observable, which does not carry its conjugate partner. So this, so if you now you can out of these families, what you can do is you can take the conjugate variable of these observables. But as I said, this entropy does not carry the conjugate partner. So this is the way how, other dimensional entropy. Yes.
Sorry, I forgot what is this ni zero in the triple. Can you just, what is the third thing in the triple?
Oh, new zero.
Yes.
It's this Liauville measure or
Okay,
Lebesgue
okay.
measure, some background measure.
Background.
You know, when you look at study the entropies, and the consider relative entropy is much more natural.
Yes.
It has, so in that regard, this whole statistical phase space has everything. Okay, so let me just repeat. The role of entropy is in the statistical mechanics derivation of thermodynamics. Points in thermodynamic phase space represent macroscopic observation of the relevant microscopic system through the averaging process. In the kinetic theory, say in Boltzmann's equations, a system is represented by a distribution density, and the macroscopic observation or the measurement in the experiment of the given system can be regarded as a kind of reduction process. So usual TPS then is the contact reduction of this kinetic theory phase space, where the Gibbs entropy function universally arises as a reduced function on any thermodynamic system. As I say, F1, choice of F1 defines some the thermodynamic system, but this entropy always enters in any thermodynamic system. Okay, and then equilibrium. So in thermodynamics, the way how the equilibrium is arrived through some constraint variation of principles. So by maximizing the entropy, you will reach to the equilibrium states. That can be regarded in this way. So equilibrium is you're given this P variable that's like the reduction of F1 and Fn. Yeah, okay. The equilibrium is the distribution rho, which maximizes the entropy under constraints of the observations of the observables for given PIs. And then we also recall the constraint, probability integral is 1 by definitions. The method of Lagrange multiplier is utilized through which the equilibrium is realized as a resemblance of manifold in TPS. So this is the, I'm just rephrasing these previous pages using the reduction I just defined. And here is the theorems, let's say. For the moment map, yeah, the reduced space is a 2n plus 1 dimensional contact manifold. Furthermore, the reduced space is locally contactomorphic to the projective cotangent bundles whose base has the coordinate associated with. So what I'm trying to say is our thermodynamic phase space is now globally defined. So through this definition, you don't need any coordinate to define the thermodynamic phase space. But to describe it, you need to choose coordinate. That's exactly what this thermodynamic textbook does. So the method of Lagrange multiply gives rise to relation. In other words, the differential of entropy should be contained in the conormal bundle of the levels of Fi. That's what this last equation, thermodynamic first law.
But the entropy is always kind of distinguished globally defined, right? Yes, it's kind of, I mean, you said there is no variable, but the entropy is there.
Yeah,
Globally defined.
comes through the reduction.
Uh-huh.
So it's, in statistical mechanics, there is some Gibbs entropy or some continuous entropy.
Mhm.
And then that is naturally reduced to some function on the thermodynamic phase.
But you are given this, you get this function globally, and I mean, this coordinate is kind of special.
Yeah, that's cool. Yeah, that's kind of special. Okay, let me summarize. So, okay, so let me just emphasize this last one. The Gibbs entropy is universal in any thermodynamic phase system. Okay? So macroscopic this Gibbs relative entropy is universally and canonically reduced to thermodynamic entropy in TPS. So associated with any observable system. And that is the source of this other dimensionality. Thank you.
Any questions?
Maybe this is a stupid question,
Yeah.
but symplectic geometry is something like energy is preserved, so it is natural that there are a lot of periodic orbit. But in thermodynamics, I think kind of energy is not preserved, so it is not natural that there is any periodic orbit.
Right.
So this why this is consistent with this Weinstein conjecture?
So this is two different, okay? So there's a background particular dynamic, Rev dynamics. That corresponds to the constant function, the dynamics associated constant function. So Weinstein conjecture is about the existence of closed orbit for that particular this dynamics. And when you turn on the Hamiltonian, then you should ask a different question. The question is whether there is closed orbit relative to this Rev dynamics. And that's one of the crucial, actually, objective study in contact topology. This is sort of translated point. In the symplectic geometry, the fixed point is something you should look for. But in the contact geometry, what you should look for is so-called translated point. So in other words, if you apply this diffeomorphism to a given point, the question is whether this image is in the Rev trajectory of the initial point. So that's in the open string version, that corresponds to the Rev code between two.
Yeah. So but then the theorem you first quoted, your theorem, says that up to some energy, if H is small, then you have a periodic code.
Not period, Rev code.
Oh.
Not period.
Oh, I see.
So Rev code between L and psi.
I see. Thank you.
So you started with the Potanian model of R3M to do all this story. But,
Yes.
But you could have started with any symplectic manifold, or?
Yeah, you can certainly do that. I mean, that space is natural phase space for statistical mechanics.
I know. But just wondering if you just take, because these are meant to be these statistical quantities, what I was wondering is about the functorality of the construction. If you just not started with just the Potanian model of R3M, but just symplectic manifolds of large dimension or something like that, how functorial would be the construction?
But the symplectic manifold is not the main concern, right? What the concern is contact manifold.
No, but these arose from the symplectic manifold by
In
taking
the
this averaging process.
thermodynamic
By
system.
taking this averaging process. So that's actually later.
Other questions?
But also contact manifolds when considered divisors and when you have Poisson structure, not degenerate, you have symplectic, open symplectic Clifton, it can behave at infinity of symplectic manifold. Can one relate to this picture?
Oh, you mean the contact manifold with the symplectic?
Yeah, it could be it should be divisor in
Yeah,
in some manifolds. And,
I think that, well, this one is something related to this. I think in physics there is some kind of quantum entanglement structure, and there is some contact three manifold with the two-dimensional symplectic horizon. I think what your question is something related to that picture. I think so. It can be. That's actually one of the things I sort of very much interested in.
Yeah, go ahead.
Yeah, so just so in the symplectic reduction, you kind of remove the group twice, so you have even dimension. So can you just comment on how you get the odd dimension here, because you need to take some subgroup and.
No, because he's mapping to the projectivization of the outer. So he's removing one less, and then the group removes.
Yeah, I can explain only through the non-degenerate, proving non-degeneracy.
Yeah, but also the subgroup, there is some subalgebra, or is it the same for the image of the moment map? There is the usual, but it's projectivized, so that's one dimension less.
Yeah, and the group is the group. So you get
And it's similar.
twice
So
the
you
group
took some
minus one.
subgroup, some H, some.
Yeah, HU. That, I mean, that's kind of, it's hard to explain. We just proved some non-degeneracy. And even in symplectic reduction, the even dimensionality is not that quite trivial to see.
Okay.
You have to actually show some non-degeneracy. And
Oh, okay. Any more questions?
I have a ridiculous question. You know thermodynamic meaning of non-squeezing?
you mean in contact case?
Contact non-squeezing. That's thermodynamic. I said it was a ridiculous question.
No, I think it's an important question, actually. You know, in symplectic, some non-triviality of the quantitative study in symplectic geometry is largely based on this non-squeezing theorem. You need to prove some kind of non-squeezing to establish something is non-trivial. So there's exactly the same question you should ask in the contact case. What kind of things actually shows what's the origin of non-triviality is exactly the question you're looking at, or the existence theorem I just proved. So, but I don't know the
Okay, let's thank you again. We'll resume in 28 minutes. Simon Center, who is going to tell us about generating functions and inverse Lagrangian forward.
Thank you very much for invitation. And also thank you very much for organizers who invite me here. And I hope that this new institute will survive and develop until next century. So something I want to talk is about generating functions. And generating functions in simplex geometry has the following meaning. So let me consider the easy case. Let me consider compact closed manifold M, and X is a point of it. And we consider some vector space, and Y is a coordinate. And we consider a function F, which is on M cross RD, Fxy. And we consider the set of all this product, so that it's Y derivative. I mean, this is all Y1, Y2, Y3, every Y is 0. And typically, this has the same dimension as M. So let me write it L tilde F. Then from L tilde F to this cotangent bundle of M, we have a map which goes from xy of this point and x and derivative of f by x at this point xy. So this is n of them. So this is a map to the cotangent bundle. And we can prove that for this standard symplectic form, dqi, and this vanishes on this for this standard symplectic form. It's just a consequence of the fact to partial derivative commutes. But I want to do it a bit more global, so I want to reformulate it in the following way. Let M be a compact smooth manifold, G be another compact manifold, which is the total space of smooth fiber bundle over M, and we consider a smooth vector bundle E on Z. And script F is a function on our total space of a vector bundle. And pi is just a composition of these two projections, so mapped to E to M. And we consider L tilde F. It's a point X on this total space of vector space, so that the derivative of F at X is 0 on the kernel in the fiber direction, all the derivative vanishes. And again, under some transversality assumptions, this is a manifold of the same dimension as M. And we define this I from this manifold to the cotangent bundle of X, M, so that X goes to pi of X is the point of M. And we take this derivative of F at X, and this bar means the following things. So we take this derivative of bar X, F, so you have this, so the X derivative of F is just the derivative of F is a map from tangent space of E to real numbers. It's a linear map. But we assume that this map vanishes in the fiber directions. So it's a pullback of the map from the tangent space of the image to R. So that is d bar x f. So we have this map I. So I is a map from L tilde f to T star n. And which is, so this is in a generic situation, again, this is immersed submanifold. And we can prove that this is again a Lagrange submanifold. And this is a very famous way and very powerful way to construct Lagrange submanifold of cotangent bundle. Maybe going back to 18th century or Jacobi or that kind of people. And this is not only Lagrange submanifold, but it's called exact Lagrange submanifold. So exact Lagrange submanifold is the following: you have this theta, the pi dqi. So this is a connection, one form on a cotangent bundle. Then if we pull back this connection form by I, you have a one form, and this f is the original function, and we restrict it, and its exterior derivative is actually this pullback. So exact Lagrange submanifold is a Lagrange submanifold, so that pullback of the connection form is just the exterior derivative of something. And in particular, d of theta this is d of theta. So this implies that the I star, d of theta, d of theta is, this is d of theta. D of theta is 0, and this is symplectic form. So this is Symmetric form put back with 0. So this is, but this is a bit stronger. So this is called exact Lagrange submanifold. And for today's talk, I want to emphasize that this I, in the generic case, is immersed. So it's not necessarily embedded. In some cases, it is embedded, but in general, it is immersed Lagrange submanifold. So let me show you some example how this kind of thing occurs. It is rather easy. So we consider M and Z to be a circle, and E, the vector boundary of circle, is just a product, and X is the coordinate of S1, and Y is the coordinate of real number, and our function fxy is y cubed plus hxy, and the graph of H is something like this. So you have a positive, and at A it gets negative, and at B it gets positive. So you consider this family of degree 3 polynomials. And then, of course, if you fix, so I'm sorry, so this is a bit small. So fixed x, we consider the map from y to fxy. This is a cubic function, degree 3 functions, and so it is it is this function. So if h is positive, there is no critical point, and if h is negative, there are 2 critical points. So this is a graph, and the condition of this L tilde f is, as I mentioned before, is the condition of here is that this condition is x on the fiber direction vanishes. It means that the y derivative vanishes. So y derivative vanishes means that here there is nothing. It is strictly increasing. And here you have two critical points. So before A, after B, there is nothing, and between A and B you have 2. So it gives you a circle.
Sorry, I'm not sure if I understand the picture. So this should be Lagrangian in a torus?
So this one is a torus, but this is a subset of S1 cross R.
Yeah, but where is the R and where is the S1?
R is 5, and S1 is this direction.
Okay.
And for each x, you have this function. That is a function of y, and you take its critical point. That gives this S1.
Okay.
Then we take the map, so the map which gives this x derivative of these functions. And if you calculate, then you have this figure 8 type things. So this one mapped to the cotangent bundle of S1, and the image of this figure 8 things. And this area should be equal because of this exactness conditions. So you have this image Lagrange submanifold, which is very typical example. Okay, now I next explain Freire-Morty, and this is in the original form Freire defined, somehow in a simplest case. So we consider Ly is an exact and embedded Lagrange submanifold of the cotangent bundle. It means that Ly is an n-dimensional submanifold of this star m, and the restriction of connection form is some d of some fy. And in this case, we just take this Freire chain complex. We just take all the maybe assume it's transversal, an intersection point, and take this free abelian group. And then the boundary operator is a kind of dp is dpq, and this guy counts these configurations. You have L1 and L2 here, and you count the strip which bounds this, and U should homomorphic. So that's kind of original definition of Freire. And so you get this map. And first Freire proved that in this situations, exact and embedded, these are the strong assumptions. In this case, there is nothing bad. This boundary square is actually 0. So one can prove it. So this is the Freire-Morty, probably in the simplest case. But it's enough interesting case. Okay. And then Freire-Morty is just a kernel divided by image. But in this exact case, I can add some structures. It is this chain complex is filtered. So filtration is the following things. So this intersection point P lies in the filter lambda, if and only if F2P minus F1P is smaller than lambda. So I mean, Fy is a kind of theta restricted to Ly is d of Fy. You have two functions on a Lagrange submanifold. And the difference is actually this gives filtrations. And if you think about the Stokes theorem a bit, and if you look at these formulas, you will find that this bundle operator preserves filtrations. So you have a filtered complex, and then you have these filtrations. So you have a two pair, A and B, and two real number, A, which is smaller than B. Then Flare homology L1, L2, AB. You take this filter B part divided by filter A part, and the bundle operator gives the bundle operator, and you take homology. So not only you have just a Flare homology, you have this, for each pair you have this Flare homology. That's a kind of used by various people to have more kind of refined information about the Lagrange summary. So now after this, I want to create. I need to assume one extra conditions. So suppose you have this generating functions from E to R. So Z is a smooth fiber bundle over M, and G is compact, and E is a vector bundle on Z. And this generating function is said to be quadratic at infinity if there exists some compact set of E, so that if you restrict F outside the compact set, and you restrict to each fiber of this vector bundle, then there are some non-degenerate quadratic form, which so F is something like a quadratic form outside the compact set, and then then change it a bit in a compact part. That is a kind called a quadratic at infinity conditions. And various people use this kind of conditions to study these generating functions and Flare theory. And the general principle is the following things. If you have a generating functions in this sense, which is quadratic at infinity, and suppose the L of F is embedded, then we can define Flare homology over L of F. And the general principle is that this is actually the most homology of the function F. So that's a kind of general principle. And one theorem which clarifies this part is the following things. So suppose M is a compact smooth manifold, and let me consider the case Z is M. So E is a vector bundle over M. And we consider F a smooth function which is quadratic at infinity. And we assume that LF is embedded Lagrange submanifold. Then you take Flare homology of LF and the zero section on the cotangent bundle. Then this is isomorphic to the most homology of F as a abelian group, which is the homology group of M. But it is something more because we have filtrations. So if you consider this Flare homology between A and B, then it's relative homology. So A is the part of the vector space where this function is smaller than A. And so this guy contains this relative homology. And this relative homology is isomorphic to this filtered Flare homology. That's I think proved by Taylor, but this kind of thing is expected, but this is some I found it in the literature.
Is this bifiltration or
Pardon?
is it double filtration or?
No, just filters.
Okay.
Between.
Okay.
That's more.
Good.
Can I make
Sure.
this theorem is proved by student thesis.
Oh, really?
Yeah.
Oh, yeah, I looked some Viterbo's paper, and he wrote his theorem. So who it is?
Milinkovic.
Milinkovic. Oh, yeah.
Not very far. We know him very well.
Sorry. Yeah, but I didn't.
Don't worry, for Bulgarians it's okay.
I'm very sorry, but I looked this so very comprehensive.
It is published in Pacific Journal of Mathematics and translated two pages.
Okay, yeah, because this is something I want to generalize, so it's very important comment. I'm sorry, I don't know so many about generating function until very recently, so I didn't. But anyway, so we consider these theorems, and actually the main goal of my talk is to try to generalize these theorems in the case where when some manifold is not embedded but is immersed. So, but before that, I need to remark that I put these assumptions here. But actually, probably this is automatic from the fact that LAF is embedded. So it seems that if LAF is embedded, then kind of, Z compact Z is equal to M. And this should follow if something called the nearby Lagrangian conjecture is true. Nearby Lagrangian conjecture says that if you have an embedded Lagrangian submanifold in the cotangent bundle, then it is Hamiltonian isotopic to the zero sections. So the degree of this map should be 1. And in general, the degree of this map should be the Betz number of the fiber of the map from G to M. So this should automatically imply that this. So and also this nearby Lagrangian conjecture implies that any embedded and exact Lagrangian submanifold of the cotangent bundle admits generating functions. But I think this fact is not true, and I don't know. Nearby Lagrangian conjecture is studied very extensively recently, but I don't know. It may not be proved in complete generality. So, in some cases it is proved, but I don't have enough information. So, please, I'm sorry I didn't say. But this condition, at least conclusion should be automatic. But my purpose today is not just embedded cases, to try to go to immersed case. So for example, if G is not M, then automatically it should be immersed. There are self-intersections. So the goal is that to generalize the story to the case when this Lagrangian submanifold immersed. So for this purpose, I want to recall immersed layer homology, which is due to Acad-Joyce. So, but I want to restrict to our case so that the immersed Lagrangian submanifold is exact. So what it means? So Li is exact immersed Lagrangians. It means that Li is immersed submanifold, but you put back the connection form, which is exact. I mean, Fi is a function of Li tilde. So in this case, let us try to define that this Freer chain complex is again this intersection point and this free abelian group generated by it. And try to define the boundary operator in exactly the same way as Freer did in embedded cases. That's possible, but then I will give explicit example later, but then the boundary square may not be 0. So this is, I think this is already known to many people, and Acad-Joyce also can study this kind of things. But one good thing is that the story I told you today gives kind of many examples of this kind of things. So what they did? So we need the notion of bounding cochain, which Acad-Joyce introduced in the immersed case, and actually with Ota Ono, we studied in the embedded case of this bounding cochain. So let me recall this story of bounding cochain and specialize it to the case of exact but immersed Lagrangians. So we consider exact and immersed Lagrangian submanifold. Then we consider this CFFI. It is a direct sum of this chain model of homology group of Ly tilde. So Ly tilde is manifold which is immersed to T star M. And the chain model is a kind of, you can choose any chain model. For example, if you fix triangulation, so you have a simple sharp chain complex, and you take CW decompositions, you have this chain model. Then you have fixed most functions, you have another chain model. Or you can take all singular chain. It's a bit huge, but so any chain model. But this part is actually not important to today's talk. There's another part. So it is a free abelian group or pair PQ. So PQ is a pair of the point of Ly tilde, which goes to the same point on a simple manifold, but are different. So it is basically this switching. So we have this. So L is something like this. Then this. So you come from this. This is I. So you have this P and Q. So this is the kind of switching point. And for each self-intersections, this is the ordered pair. So for each self-intersection, you have 2 points, PQ and QP. So that is the CF, Fy. And in our exact cases, we can decompose the switching part into 3 pieces, positive, 0, and negative. So positive means that f of p is bigger than f of q. 0 means that f of p is equal to f of q. Negative means that f of p is smaller than f of q. So you can decompose into these three things. Then we consider B, it's an element of the switching part, finite sum of the switching part with integer coefficients. But we consider only the positive part. So the pair we take has a kind of Fp is larger than Fq. Then I want to use it to, so this is the original Freya's boundary operator. And using this boundary cochain, I want to deform this Freya chain complex in the following way. So let me record that this original boundary operator Freya count the configurations which I draw here. You have this P and Q, and you just take this strip, and L1 and L2. And but then if you deform it, we include this kind of configuration. So this happens to be 3 switching points. So you have a strip, and this boundary go to L1, but you allow this it switches at the point of self-intersection. And this also you allow switches, and this allow switches. You allow arbitrarily many switches. So that's what this counts. But we count this with some multiplicity. So multiplicity is the following thing. So B1 is bounding cochain. So it is a sum over Pi Qi with integer coefficient. So B1 Pi Qi is an integer. And this non-zero only in case this is positive. And B2 is also Pi prime Qi prime, B2 Pi prime Qi prime. So we have this integers. That is information for this bounding cochain. And then we have this kind of configuration. So here we have switching from Pi to Qi. Then we put this B1 Pi Qi as a part of the weight. And here you have this Pj to Pj prime to Qj prime and Pk prime to Qp prime. Then we take this B2 Pj prime Q prime, B2 Pk prime Q prime as the integers, and we multiply this. So this is all 3 switching, but you have 10 switching, then you multiply 10 things. 1 switching is just like 1. No switching, it's 1. So you have this sum of weighted sum of all these configurations. And in
these are weights and integers?
Integers, in an exact case. And using this exactness and the positivity of the switching, positivity of the bounding cochain, you can see that this is a finite sum. It's a kind of energy estimate. So this is a finite sum. So you have this finite, this is the integer. So we have this boundary operator, CF L1 L2, CF L1 L2. And as I said, non-coupling, we don't need non-coupling because everything is exact. And so now we ask that, so now after these collections, it is, the square is 0 or not. And it is not free, but this holding is BI satisfies a certain algebraic equations called the Moller-Cartan equations. An example of Moller-Cartan equation I will explain below later, but here I just mentioned that there is some particular equations, so that it implies that this boundary square is 0. So we call this BI is a positive bounding cochain if it satisfies Moller-Cartan equations. So this is plus. And this kind of positivity kind of works only in a case, exact case. In more general case, like Akaho-Joyce and FO cube, we just take infinite sum using Noble coupling. But in this case, we can just work on this positive things. Okay. So now this is a definition.
Oh, sorry, can you,
yeah.
Sorry to bother you. There's also something about spin structure.
Yeah, I'm sorry, I forgot.
Is it automatic?
No, it's not automatic.
Ah,
Yeah,
so
we assume everything is spin. Yeah, I'm sorry.
Even
Yeah.
for this
You're
general
right.
functions.
Yeah.
Okay.
So suppose we have this positive boundary cochain, you have this boundary operator, and you can define Freya homology using in a natural way. And also, using the fact that this B1, B2 are positive boundary cochain, this filtration is also preserved, because you switch it, it's always F is increased. So, this preserves filtration, then we have this AB version is defined, right? FB chain complex divided by FA of chain complex and the boundary operator preserved. So you have this filtered Freya homology under the presence of boundary cochains.
Is the thing that you're describing identical to linearized Legendre contact homology?
Probably it is related. But
It seems just identical.
let me see. Probably.
They're related. The redirected Lagrange motion can be
Yeah. I think it is related. Yeah. It's basically the same thing. But usually those people use dual language, right?
Yeah, maybe.
We use AB algebra, they use DGA.
Yeah.
But that's dual. Yeah. Okay. So and I want to mention that 0 is a positive bounding cochain if there is no teardrop. These configurations. So this configuration that you have this you have this some strip and just have one switching. And if there is no such a switching, then 0 is actually a bounding cochain. But if this is 0, but if this, then it is not a bounding cochain in general. So now after all said, I can state my theorem. My theorem is the following thing. Suppose M is a compact smooth manifold, and E is a vector bundle over fiber bundle. And you have a F smooth function, quadratic at infinity, and we consider LF, which is image, and maybe spin. And then first claim is that this guy has a positive bounding cochain. So that's first claim. And this positive first bounding cochain is somehow canonical. Canonical means that there is a notion of gauge equivalent of Mohr-Cartan element. You know, the Mohr-Cartan equation is something like a flat bundle, flat connection. So you can define gauge equivalence of flat connection. So there is something similar for the bounding cochain. So there's a canonical choice of bounding cochain, which depends on them, but it depends on all other kind of choices. And the third thing is that so you use this B to correct this boundary operator. And 0 section is embedded and exact, so you can define plain homology. And that is the most homology of F. And this filtered version is true. It means that this B version is equal to this. So this is exactly the same as the theorem I wrote before, except we have this statement about the bounding cochain. Now I want to do some example. So let me consider this example we did before. So suppose that M and Z is S1, and E is S1 cross R, and you have this fxy. Y is the cubic functions, which has this kind of first order term. And then as I explained that this L tilde F is S1, and the immersed one is this figure it forms. So let me try to think whether this guy has a bounding cochain or not. And this guy has two teardrop, red one and green one. So there is something called the curvature M01. That is actually a count of the teardrop. And actually this cancels. And one important thing is they have the same volume. And the output is both are positive. So you have the same output. And orientation is a bit delicate, but I'm pretty sure that this cancels. So so even though there is a bounding curvature, but teardrop, but two teardrop just cancel out. So 0 is a bounding cochain. But that's not so much illustrative. So I want to explain the case when bounding cochain is non-zero. So we consider again S1, and E is S1 cross R. Then now we consider this kind of sequence. Probably you can cook up that thing using the polynomial degree 4. So first you have this thing which has only one minima, and you have a bond of pair of critical points, small and big, and then this one move here, and then you have another picture, and then you die out. So this is a typical kind of bifurcation diagram of the family of functions. So now, so if you consider, this is the picture of L tilde F. So here you have only one, and here you have only one, but in between you have three, and then they are joined in this way. So now I want to calculate how this, I want to see how immersion looks like. And I think you just take very naive but very easy choice, it is just embedded. So it's not interesting. But you can make arrangements so that it has actually these two self-intersections. Something like this. And what is important is that you have these two domain, which is encircled by these configurations, and you compare the area of A and B. It is easy to see that A is smaller than B. This is a good exercise. You can try to prove it. Suppose you have a family of degree 4 polynomials and you have this picture, and this area A is smaller than area B.
But you assume that it totally emulsifies.
Yeah, it is coming from the family of most one parameter family of most functions. And on one parameter family of functions, you have some critical parameter. But this is smaller than A and B. So we consider this picture. Then so what is this? So you have this one teardrop. This is something called M01. It is a curvature. But then actually this another intersection point is actually our B, boundary cochain. So why this? So you consider the boundary of this B. Boundary counts hallmark strip, and you can see this blue hallmark strip. So M1B is M1B and M01 is just the same thing. So they cancel out. But actually this condition A is smaller than B is important, because let me remind you that this self-intersections corresponds to generator in a flares in the upper complex. And which one goes this way? One of them goes this way and the other one goes this way when you take boundaries. And which one is positive, which one is negative, is actually depends on the sign of A minus B. Actually, you can see that FP minus FQ is actually the area of this guy. It's against Stokes. And that is A minus B. So with A, and in case A is smaller than B, then that generator goes this way. Positive generator goes this way. And this formula is satisfied. And this is actually the simplest part of this infinity formulas. And the monocarton in infinity cases is just like this. M01 plus M1B plus M2BB plus M0. And again, in our exact situation, this is finite sum and well defined. But in our case, there are no higher term just does not exist. M01 and M1B is monocarton. So you have a solution of the monocarton equations in this case. So that is particular case of this theorems. And so the theorem says that this kind of phenomenon happens in where any immense Lagrangians which are the genetic functions. So let me mention the corollary of theorem. The corollary of theorem is the following thing. If you have a L, which is an exact immense Lagrangian submanifold, and suppose it does not admit positive boundary cochain, then there is no genetic function canonical at infinity which gives L. And I think there are some problems for given Lagrangian submanifold if there is a genetic function globally. And in the case of embedded Lagrangian submanifold in a cotangent bundle, maybe this nearby Lagrangian conjecture gives the solution. Because I think it is the theorem that the existence of a genetic function is invariant of Hamiltonian isotropy. So it means that I don't know how much it is proved that if nearby Lagrangian conjecture is true, then any embedded Lagrangian submanifold in a cotangent bundle admits genetic functions canonical at infinity. But in the immersed case, so there are some conditions, purely topological, algebraic topological natures. If you have any immersed Lagrangian submanifold, then whether it admits genetic functions is a kind of problem of algebraic topology. But those genetic functions may not be canonical at infinity. So you cannot globally study that kind of things. And if you put the condition that it is canonical at infinity, I don't know how much it is known, because I don't take so much time after studying this kind of things. There might be something known, but I don't know how much it is known. But this particular theorem gives some obstructions. And actually, I don't know. So now it implies that in this S1 cross R cases, you have this kind of Lagrangian submanifold. This guy, the A is bigger than B. And the theorem says that they don't admit genetic function canonical at infinity. And I tried to prove this without using a Holmont curve, and it seems possible. Yeah, I didn't check in detail, but probably one can prove it because this doesn't admit genetic function at infinity using just a Moss theory. And that's a good exercise. Maybe it might be fun to do it. And it is not surprising because as you know that many theorems in symplectic topology in dimension 2 or 1, you can prove by very elementary things. But if you go higher dimensions, the same thing required to use the Holman curve. So I think if you take this, at least the third example, cross, so you consider S1 cross Sn, for example, then this guy plus cross 0 sections. Then one can prove that it doesn't admit a generic function canonical infinity. And it is much challenging to show that statement without using Holman curve. And maybe it is impossible. I don't know. But at least I cannot do it. So that gives some non-trivial obstruction for this, for the immersive Lagrange to have generic functions. Okay. Yeah, and I just look at this example, so I want to explain how this positive bounding cochain corrects the Freir's differential so that the boundary square becomes 0. So this is the kind of simple example. So I think this kind of example is usually difficult to cook up, but this example I can explain. So probably Acad Joyce did not notice this simple example. So you have this L, so you have this L, black one. I'm sorry, this looks bigger than this, but this is actually smaller. So this is L, and we have an L prime, that is this blue, you have go like this. And you have 1, 2, 3, 4 points intersecting this. So this is the generator of the Freir's chain complex. So I want to calculate Freir's boundary operator. So first, we don't put bounding cochain. So we start this intersection point W, and we want to calculate the boundary operator. So we have this yellow strip, which is from W to Y, and I think there is nothing else. So the boundary W is Y. Then next start with from Y. I have this blue strip. Then the boundary Y is Z. So if you take twice with the boundary of W, then it is Z, and it's not 0. So this is the kind of typical way that the Freir's, in most cases, Freir's boundary operator is not a boundary operator. And you can see that this teardrop is the reason that this phenomenon happens. So now I want to put boundary cochain here. So it means that you are allowed to switch from here to here at this point P. So now I want to calculate the boundary of W. So one is Y before, but then you have this triangle. And this triangle may be regarded as a strip from W to X with switch at B. So you have this another term. And I never understand science so much carefully, but science should work. And this is exact, so if science does not work, you can just go to the zeta coefficients. So it's not so serious. Then next we calculate the boundary of X. Then we have this red strip. So boundary B of X is Z. So you have this Y, so then you have this square, then this Y goes to Z and X goes to Z. So they cancel. So after putting this B, then you got this boundary operator. So you got very defined Freir homology. So that I think is this particular example, rather simple example. And it is expected to hold for any Lagrange manifold with generating functions. Okay, so now, let's see, yeah, before explaining a bit about the proof, I want to explain positive relation to shift theory, because this relation to generating functions and Freir homology is somehow related to sheer theoretical understanding of Freir homology. I think what people did in this kind of situation are the following things. You put L hat F, it is a Lagrange submanifold of cotangent boundary of M cross R. So you get X, so this part is a cotangent boundary of M, this part is the cotangent boundary of R, and X, D bar X F is this L of F. So then, in this second factor, you take this critical value F of X, and you allow lambda here. So you have this Lagrange submanifold, and what's good is that this is kind of conical. It means the invariant of R plus actions on a fibers. And I think it is known that there is some objective derived carnival coherence shift on M cross R, and something which is called a singular support is this Lagrange summary. And the story, which is kind of studied by various people, is that most homology of F and shift homology of F of F and Frey homology of L of F, they are supposed to be the same. But I think people so far study the case of embedded Lagrange summary for LEF. I'm not so much sure. Even in LEF is embedded. This one is this is immersed. This one can be embedded. But this self-intersection corresponds to some Lev code, right? Or this kind of thing. So I don't know how it's related. But I am still a bit puzzled what is happening. Yeah, maybe it is better to explain this immersed cases. In the immersed case, what is happening? This kind of things. An example is actually a very easy example. So let me take an example. So in this case, we take M as point. It's very easy. And Z is a fiber band of a point, so Z is a closed manifold. Z is a closed manifold, compact. And E is Z, so there's no vector boundary things. And we consider F from Z to R. This is the most functions. So let me consider this very easy case. So what is L of F? L of F is just a critical point set of F, right? So L tilde of F is a set of critical points. This is a finite set. And then this is immersed to this T star of M, and this is just a point, right? M is a point, T star of M is a point. So you have a trivial simplex manifold, just a point. And you have a finitely many points which goes there. That's a Lagrange submanifold. But then what is B? So B is actually a boundary operator of most complex of F. Remember that B assigns integer to each pair of to each self-intersection point. In this case, self-intersection point means that you have two different critical points. And positivity means that the value of F is bigger than the value of F. So you can count the number of gradient lines. That is actually B in our cases. And so this shows that if you have a B, then it's a bit too much degenerate. Frey homology is actually most homology. So this is a kind of very much degenerate case, but it does just like that. And I can say also this F of F. What is F of F? So this is a sheaf. Object of the category sheaf on this real line, right? Because M is a point. And then so you take a lambda in R, then this stack is I think homology of Z lambda. So you have a family of homology groups, and so this is the kind of picture, and you can see that this homology jumps when lambda hits a critical value, and that is exactly this L hat F. So that's in this degenerate case. And in a more general case, somehow it is the family version of this story. You have an M and you have a cotangent bundle. And then this most boundary corresponds to something like a boundary cochain which lies on a self-intersection on this locus. So some puzzle I'm just still not completely understand is that in immersed cases, whether this F of F knows boundary cochain or not. If you look this, so I mean, if you have this kind of filtered homology, then can we recover this most boundary operator from this? It seems that, but I am a bit still puzzled. So whether this, so you consider this guy. So this guy, you have to do this guy plus boundary cochain. So LEF alone does not give this sheaf. I mean, I can explain it because by this, so the next remark. So next remark is the following things. If LEF is embedded, then this determines F up to stabilization. stabilization means that in the case G is M, you add some vector bundle and put extra part is just a positive definite quadratic form, non-degenerate quadratic form. You can increase variables in that way. Then after that, you just transform by the vector bundle isomorphism. So that's the stabilizations. And it is Viterbo, it's okay. Viterbo knows that he proves that this embedded Lagrange sum manifold determine this generic functions up to this stabilizations and isomorphism. But I can say that this statement is definitely wrong in our immersed cases. So we can actually easily construct a pair of these generic functions, which gives exactly the same immersed Lagrange sum manifold, but the most homology of F and G is different. If you want to consider such example, so you can just take G is, you can just take M cross N1, M cross N2, and Fy is basically the most functions on Ny to R. It is composite. And then this immense Lagrangians, just remember how many critical points this Fy has. So you take two manifolds which are completely different batch number, but you choose your most function so that the number of critical points is the same. Then you have this. But of course, this most homology is just the homology of this. So they can be different. And what happens in this case is that the bounding cochain is different. And this bounding cochain, in this kind of situation, again, this boundary operator of this most homology. And it's not a direct product, but we have a cell spectral sequence, and it's differential with this bounding cochain. So in this generality, this immense Lagrangian does not determine F. So you have to say that, and I don't know, it's a bit too much to expect that if this is true and the boundary chain coincides, then F is equal to G. Probably it is not true, because you can take this kind of pairs, and Ny and N2 for example, not diffeomorphic or not homeomorphic, but have the same homology, then you cannot expect this kind of thing. So I don't know, but at least at what level of homology group, you have to include some information about this bounding cochains. And I looked at other papers by Viterbo. There he starts from embedded Lagrange sum manifold with the cotangent bundle, embedded exact, and do some grading analysis to obtain this sheaf, L of F. That's at least object of derived category in some papers. That's kind of family of Frey homology type argument. And I believe if you have a immense Lagrangians plus bounding cochain, probably family of Frey homology gives this sheaf F of M. So at least the sheaf theory and this immense Lagrangian with bounding cochain probably is somehow very much related. Okay, so now that's the story. So now I want to say a few words about the proof of this main theorem. Actually, this is related to some theorem which I proved 5 years ago. So that's related to this Lagrangian correspondence. So the theorem is the following thing. Suppose you have this L1, which is a Lagrangian sum manifold of compact symmetric manifold X1. And suppose you have L12, which is a compact Lagrangian sum manifold of the direct product of minus X1 cross X2. Minus X1 is X1 with opposite symplectic form. And then we take this Fire product, and L2 is the Fire product of L1 and L12. And in a generic case, this is an immersed Lagrange sum manifold of X2. And the theorem says that if we have a bounding cochain of L1 and the bounding cochain of L12, then it gives a bounding cochain of L2. In some sense, canonical up to gauge equivalence. And so now, our situation actually is very much similar to these situations. Mostly the same, but somehow different. So let me consider this immense Lagrangians. And it is actually obtained by Lagrangian correspondence. So one of them is a graph of this D of F, which is the exact Lagrange sum manifold of this tie. And another is this guy. So this guy is the following thing. So Xc is an element of cotangent boundary of E. The Y mu is an element of cotangent boundary of M. And we assume Y is an image of X. And Xc is a pullback of B. This is some kind of conformal boundaries, and you can easily check that this is a Lagrange manifold. But it is exactly the definition that if you take the final product of this guy and final product of this guy, then you get this error wave. So, and then they both are exact. So 0 is a canonical bounding cochain. So we can, if we apply these theorems, we can prove this main theorem. But it's not such easy. There are two things one need to think about. One is that here everything is a bit non-compact. So this Lagrange manifold is non-compact. And D of F is non-compact, and even worse, that E itself is non-compact. So I need to use this quadratic at infinity condition somehow clever way. And so that this argument goes through to get this bounding cochain of the error F. And also, we don't claim not only exists bounding cochain, but it's a positive bounding cochain. It's a very special form. It is supported on a switching component, but also on positive part of the switching component. But for this, we need to see the proof of these theorems. It's actually a bit lengthy. This paper has several hundred pages, but you just look at the proofs, and so since I have a bit less than 10 minutes, I want to explain some of the proofs. So that's the following things. So we can consider this strip. And so you have this map U1 and U2, and this U1 goes to this T star of E on this first factor, and U2 goes to T star of M. And here, this line you require that go to this graph of DF. And this part, I think I cannot write it, but this Lagrangian is required to go.
It's kind of a normal bundle to the graph of.
Yeah. And then this side is required to this error wave. So you consider this kind of configuration. This is called a pseudo-Holmov quilt, which is studied by these people, which I told before. Yeah, these people, Wilhelm Woodworth and Mao and Botman, they studied this pseudo-Holmov quilt to study the story of Lagrange correspondence. And everything is holomorphic. And then you consider this limit. And we require two holomorphic curves, and here there are some matching conditions which rely on this Lagrange manifold. And then you go to minus infinity and plus infinity, and then this limit is something like a LF tilde. So you put some boundary conditions here, and you count it, and then something we can do is the following thing. So we have chain complex of LF tilde is a chain model of LF tilde plus switching. And we take this fundamental class of this LF tilde, diagonal part, and I want to equate that the fundamental class should be so this gives actually some bimodule, at least the right module of this Lagrange manifold. So and then I want to require that this diagonal is a cycle with respect to this boundary operator, and that uniquely determines the bounding cochain of here. But then we need to think somehow carefully how this, which kind of output it can just using this energy estimate. And this is a proof in case E is Z. I mean, in case E is Z, so something is rather hard in the compactness. So in the case E is Z, the D of F is compact. F is a function of compact space Z. So this is compact, but immersed. And this is actually non-compact, but it's not so bad, it's a kind of conformal bundle. So you can work out the analysis here. If E is Z, but if he is not Z, then this guy is already non-compact, and this is immersed, so everything is much worse. So I want to, in this case, I will modify the problem accordingly. So E is a vector bundle. over Z. And this is E plus and E minus. What is E plus and E minus? We assume our function f is quadratic at infinity. It means that it's a quadratic form which is non-degenerate. So you have a positive definite part and negative definite part. So this is the direct sum decompositions. And then I want to kind of E neighborhood of infinity, embed it to this sphere bundle. Yeah. So over Z, you have this 2 vector bundle. And you include it to this sphere bundle. And then you take the fiber sum. So this fiber is something like a Sn cross Sn. And this is quadratic infinity, so you have this Sn, and this compact part you don't know what happens, but this is very close to infinity. So you have, so you can just modify it so that critical part is very big. And this is plus part. The minus part you have this modified. You have this something finite, and this is very big negative. So we change the situations so that E is become compact. But then you have another critical point which lies on this positive, which has a 4 points. So S2 cross Sn cross Sm has 4 critical points. And this is finite part, but you have this 3 part which is infinite, minus infinite, minus infinite, minus infinite. But then one can observe that they are kind of the value of most functions on these 3 points are very big in energy by choosing this way to modify your functions. So if you consider this modified f, you have some critical point whose value is very big. You have some critical point whose value is very small. And on the boundary part, you have exactly the same thing, an original. So once you have this guy, then we use the fact that everything is filtered, so that this finite part, you can just take this finite part to get something you want. So that's a bit more technical, but it's not really very difficult. So yeah, so now that's an idea of the proof. Okay, so now I'm almost finished. So thank you very much.
Any questions?
Yeah. It means that you make your kind of auxiliary spaces like vector bundle, some compact manifold, and some quadratic forms of degrees. There's a better way to maybe have manifold with a boundary, and boundaries still decompose in positive and negative parts, so it's a bit more generous. And you mentioned like a function of the complement to the boundary goes to infinity and positive part minus.
Yeah, but then this way you have this kind of spheres which are closed up. So you have just a boundary.
Yeah.
Then you have some your manifold.
Yeah, no, but you should kind of through the generalization of such kind of a function.
Yeah, I have to think about it. I don't know how much it works.
Yeah.
Probably it works. I mean, the example of this y cube plus something is something as you mentioned. And at least that case works. So it might work, but I have to think very carefully. That's very delicate things. And the point is that this is quadratic at infinity, and if it's definite, then you can just plus infinity. But in indefinite, you have a plus infinity, minus infinity, kind of intermediate part. So it's a bit more subtle.
I actually kind of thought a little bit about more serious than that's what's kind of.
Yeah. But it might work, but I never thought seriously.
So I think this discussion about inductive Lagrange motion is part of this general Legendre manifold in the one-jet bundle.
Yeah.
So maybe this whole theory can be applied to the Legendre manifold that admits general function.
I mean, so I think this theorem. This theorem, this is about Lagrangians, and it is likely that this theorem we can generalize to Legendrians.
But for the Legendrian case,
one could also use augmentation variety. Bounding quotient is kind of equivalent to augmentation.
Yeah. I mean, it's just a change of language. I mean, this exact kind of situation, it's completely dual, right? You have a finite list. So the APT and the DGA actually is basically the same thing. And so you just translate the language. But I don't know how much it is studied. Are there any theory of Lagrangian correspondence or
Yeah, here is the question is whether this how you can prove this augmentation is non-empty.
I mean, so this one just says that there's no emptiness of augmentation is preserved by augmented correspondence. And in a special case of the generating functions, then you know those two, which start with the exact Lagrange sum manifold. So 0 is automatically bounded quotient. But 0 gives something which is not 0. So that's yeah. So you start from some 2 Lagrange sum manifold, which is 0, which has 0 as a bounded quotient. But you take Lagrange correspondence, you have some immense thing, for which you have a non-zero bounded quotient.
So the question is, does this bounded quotient augmentation is non-empty for the Legendre manifold admitting this general function?
Yeah, I mean, I don't know how this proof can be applied. I have to think very carefully. But it might be possible that that kind of, I mean, what I mean that Legendre sum manifold with generating functions can be obtained from something exact, I mean, more obviously augmented by correspondence. That I didn't think so much. And one thing is that this story gives actually many examples. For example, if you want to get some, if you want to obtain some Lagrange immersion sum manifold, which is immersed but has a non-zero boundary quotient. Usually it is very difficult to cook up examples. We try much, but this generating function things makes as many examples as you want. And also, I mean, there is some question in the case of monotone embedded things. If you have some manifold, you compare Frey homology and naive intersections. And there is a case that they are actually different. For example, the Frey homology is non-zero, but it's not isomorphic to the original homology group. That's difficult in general. But if you go to immersed world, so this kind of example gives you have a huge number of examples, so that this L over F itself is very complicated, but the homology is small.
Any more questions? Let's thank Kenji again. Resume at 4:45.
Yeah.
dots.
Okay, let's start with our last talk for the day. John Totten from Princeton is going to tell us about co-shifts of Rapp-Fukaya categories.
Thank you very much for the invitation to give this talk. This is my first time in Bulgaria. I'm going to be here. So everything I'm talking about today, this is joint work with Shilga Natra and Vivek Shande. Okay, so let me begin with a few basic definitions for the sort of objects I'll study. So, an exact symplectic manifold is a manifold equipped to one form, and that one form is called lambda. D lambda is supposed to be symplectic. And this is called the Lagrange form. Now, giving the data of this Lagrange form is the same as giving the data of the symplectic form and this vector field, which satisfies LC omega is omega. So that is to say, when you flow under the flow of the vector field and pull back the symplectic form, it gets scaled. So from that relation, you know that omega has to be trivial in Durand cohomology, because diffeomorphisms act trivially on Durand cohomology, and they also scale omega. Okay, so that's, and of course having one form of d omega equals d lambda also shows it's trivial cohomology. So that means the symplectic manifold has to be non-compact, because otherwise you could write this and then you see omega is not.
Can you speak up a little?
Yes. So these objects are nice for doing third theory, and we need a little bit more control though, because of the non-compactness. So we need some control at infinity, and so this leads to the notion of a Liouville manifold. So a Liouville manifold is one of these exact symplectic manifolds, which is cylindrical at infinity. So you might draw it like this. It has some topology. Now there's a compact submanifold with boundary. So this is the Liouville manifold. Call it X. What we ask is that there's some X0, and that's a compact manifold with boundary, and the vector field should just be always outward pointing along the boundary. And moreover, if you follow the flow of that vector field outside, then that defines a diffeomorphism between this boundary across the half line and the rest of X. So that gives you some control at infinity. And it expresses, well, it puts the boundary of X naught across R inside X. You can flow both up and backwards. And the complement is some singular subset called the core of the Liouville manifold. Okay, so on Liouville manifolds, we usually talk about cylindrical objects. Cylindrical just means invariant under the Liouville form, near infinity. Okay, so some examples. Cotangent bundle is a Liouville manifold. A Stein manifold is a Liouville manifold. A closed analytic submanifold. That's not quite right. This one's a closed analytic submanifold of Cn might have sort of infinite topological time. So it's not cylindrical in infinity. Rather, I should say that it can be exhausted by these sort of convex subdomains. If you have a Liouville manifold, you can add a handle to it. So if I want to add a smooth handle to a manifold with boundary, I need some dimension, and I need a parameterized sphere in the boundary with a framing of the normal bundle. To add a handle to a Liouville manifold, there are two things I need. I need the dimension of that handle to be most half the dimension of the manifold, and the attaching locus had better be an isotropic submanifold of the boundary. So in that case, you can add this handle, and in fact, the theorem of, I'm not sure whether I should just say just Eliashberg or Chili-Beck and Eliashberg. But it's a theorem that anything you get, or anything a Weinstein manifold. So what's a Weinstein manifold? A Weinstein manifold just means you start with the empty set and add Weinstein handles. So it's 0 handles, 1 handles. And, so it's something you get only by using this handle construction. Anything, and any Weinstein manifold is a sign.
Could you just show some handle on this picture?
Yeah. Yeah, so let's see, I guess it's a little bit, yeah, so to add the handle first, first it's better to truncate off the infinite end, and then you have this thing, so you add your handle. And the Leva vector field, it has 1, 1, 0 here. So it looks sort of like that. And then you can complete back again if you like. So if you write down what this local model has to be, then you see this. So there are not so many examples of non-Weinstein Leva manifolds. There are some. I think the first one was from McDuff, but there are others now. Basically, the way you show Leva manifold is not Weinstein is you show its homotopy type cannot be obtained with just half-dimensional handles. But for the most part, we're happy understanding Weinstein manifolds. Okay, so the invariant I want to study here is the Rapp-Foucault category. So what is that? So the objects, the category are Lagrangian submanifolds, which are cylindrical at infinity. So maybe I should use a different color. Something like that. Everyone already knows what the third chain complex is. CF of two Lagrangians generated by the intersection points with the differential counting holomorphic curves like this. There's a new element in when you have non-compact Lagrangian submanifolds, which involves wrapping. So that is, you take the Lagrangian at infinity, and you flow along a vector field tangent to the boundary. So in the case of, say, cotangent bundle of the circle, you take your cotangent fiber, and you wrap it like this. So you create this infinite rank. I think that's this example here. Yes. No, so in fact this is Ezra. This is a category. Composition counts. Lagrangian boundary conditions. And so, take a Lagrangian itself, let's see an algebra.
So what is the product structure?
Sorry?
The product structure?
It's the Lorentz.
I mean, like on the picture.
Yeah. So, right. So the product structure is you count holomorphic disks with 3 boundary
Yeah.
things. And these are the 2 inputs and that's the output. So then you have to figure out what that is. You can lift to the universal cover and there's sort of one obvious triangle and nothing else. Okay, so I have the attribution wrong on this, or not completely correct on this next example. In the cotangent bundle, the graph for homology of the fiber with itself was proven by Acad and Schwartz to be isomorphic to chains on the base loop space of the manifold. And Apuzade showed that the fiber generates the whole category. So once you know this, you have the categories. Okay, so the next thing I want to talk about is Liouville sectors. So Liouville manifolds are nice object to consider. They're sort of discrete sets. And so often we try to calculate invariance by relaying the value of the invariant on one thing to the value of the invariant on some other things. And so Liouville manifolds are hard to relate to each other. So a Liouville sector is what you get, but when you chop up a Liouville manifold into pieces. Okay. So what you would naturally like to say is, well, let's just take the definition of a Liouville manifold and allow some boundary. So then, for example, maybe a cotangent bundle with a manifold with boundary would be one of these things. So that doesn't work because when you count your holomorphic disks, the disks could approach the boundary. And that destroys all the structure that allows you to form your invariance. So there's a condition on the boundary, which makes things work. So whenever you have a hypersurface in a symplectic manifold, it has a canonical foliation called the characteristic foliation. That's the kernel of the restriction of the symplectic form. And there's a general principle that if you're counting holomorphic curves and you do a next stretch along a hypersurface, then in favorable cases, those holomorphic curves will try to concentrate along closed orbits of the characteristic foliation. So that's not quite true in general, but it's true for stable Hamiltonian hypersurfaces. Anyway, I'm just using it as motivation. So the condition of being Liouville sectors, there should be a function on the boundary such that when you restrict it to the characteristic foliation, its differential is positive. So this definitely means you don't have any closed orbits in the characteristic foliation. It's a strong version of that statement. So that's maybe one explanation for why this is a good condition.
Sorry, what was Z?
Z. Yeah, so Z is the Liouville vector field. So this is just some, in fact,
This is on the boundary. Sorry. So Z is not on the boundary, right? This is on the.
Yeah, right. So yeah. So let me draw like a Liouville mount. It's a Liouville mount with boundary. So here's so the Liouville vector field does something like this. And when I see say a Liouville manifold with boundary, I want the Liouville vector field to be tangent to the boundary outside compact set. So you flow along the vector field here, and you get this infinite cone over the boundary. And there are two types of boundary, which is a little bit confusing. So this part of the boundary here, this is what I would call the sort of true boundary. And then there's this sort of asymptotic boundary at infinity, which another color. And this function, it's just defined on the boundary. So it's something you can just write down in lots of cases. You want to prove something, write down your function and show it satisfies this property. Now, to actually use this condition in practice, you want to use an equivalent formulation, which is that a function I is the same as boundary neighborhood coordinates of this form. You're just factoring off a copy of the potential model of the half-line from your manifold. And this form also suggests, this is the easiest way of proving the holomorphic curves don't cross the boundary, because you choose a product almost complex structure. This becomes C and use the open mapping principle. Okay, so this is basically an immediate corollary of what I just said. Once you show that your holomorphic disks don't approach the boundary, then the Raphel category works. It's defined for lethal sectors. Now, the fact that it's a covariant functor is a new phenomenon for lethal sectors. You can have inclusions of lethal sectors. So, for example, the ball inside a manifold in G star. The ball includes into G star Q, so you have a map like this. And this is just pushing forward the graph. Okay, so we want to understand how these categories fit together, relate to each other. So first, what is the core of a Liouville manifold?
Sorry, so the morphisms are just inclusions. That's what.
Yes, just inclusions. Yeah. So it would be nice to have more morphisms. Like, I guess Lagrangian correspondences would be maybe the best one to hope for in terms of morphisms.
Because we were talking about like cutting the Liouville manifold into pieces. So.
Yeah. So each of the pieces includes into the whole space.
But you cannot like communicate between the neighboring.
Yeah. What you would do is just say the intersection maps to both of them.
Okay.
Okay, so I already defined this. The core of a Liouville manifold is the set of points which don't escape to infinity under the Liouville flow. So I have some examples here. Yeah, okay, so if you're on a cotangent point of the core, it's just a zero section. That's sort of an outlier. Usually the core is pretty singular. The core has volume zero always, because you take any Liouville domain and flow down by the Liouville flow, the volume goes down. The core is the intersection of all those. So whenever you add a handle has a core and a co-core. The core is this stable manifold, the downward flow of the critical point. And the core of a one-steam manifold is just the union of all these cores. I guess that justifies the name core. Okay, so the core sort of contains all the symplectic topology here, or at least, not the core as a topological space, but the core together with its germ of thickening into a symplectic manifold, embedding into a symplectic manifold. That's sort of a tautology, right? Because you can take any Liouville domain and just flow it down until it's a small neighborhood of the core, and then complete again. So in some sense, maybe the core is a more canonical thing to study, or a simpler thing to study. But the problem is, though, it's singular usually. So that's what I just said. Okay, so there's this conjecture of Kontsevich, which says that the Raphel category is the global sections of a co-sheaf of A infinity categories on this core, as long as the core is isotropic. Now, this covariant functoriality of the Raphel category for Liouville sectors is saying you have a pre-co-sheaf. Not quite a pre-co-sheaf on the core, but something slightly different. Okay, so first, it turns out to be easier to prove a property like this if you change the statement a little bit. So that's what I'm going to prove. Well, I won't prove it. That's what I'll state first, and then I'll say how one could try to rephrase it in a way which is closer to this desired statement of having an actual Cauchy bundle before. Okay, so here's a naive attempt to reformulate the conjecture. So it's just take a cover by the sectors, and you look at these multiple intersections. So this is x1, this is x2, and this is x1 intersect x2, and maybe x is the union. So then, if you had a Cauchy, you'd have this Meyer-Vietoris property. So let me just.
This of course, this Lewis sectors just open domains.
Yes. Sorry?
Yeah, do you think correctly? This Lewis sectors is like non-compact cores. It's open domain, in open domain.
I mean, you should think like an open subset of the core, so if you take the fiber.
Yeah.
That's the inverse image of it. Yeah.
It's cylindrical.
Yeah. Okay, so in the case of a two-element covering, Cauchy property is telling you want this to be a push out, Meyer-Vietoris property. So knowing these three categories tells you this. So there's a problem with the statement as I phrased it, and that is that the intersection of Liouville sectors has no need to be a Liouville sector. So to be a Liouville sector, there's this condition on the boundary. You had to have this function. Equivalently, you have to have a Hamiltonian vector field, which is outward pointing on the boundary. And if you have a Liouville sector, there's no reason. The intersection should also be a Liouville sector. So that the answer to that problem is a definition. So here's a definition of a sectorial covering. So sectorial covering just says we have nice coordinates near all the intersections of the hypersurfaces. So if we cover X by Liouville sectors Xi, then this system of hypersurfaces, all of their boundaries, should admit local coordinates of this form. So you should think back to when I defined a Liouville sector. I basically said a Liouville sector is when the boundary has coordinates of this form, k equals 1. So this is the natural generalization of that statement. If you have k intersecting hypersurface, then you say hypersurfaces, then you should be able to split off a T star RK. So incidentally, this means that you can have at most, n intersecting hypersurfaces if X is dimension 2n.
John, can you say, is there a conceptual way to see this in the mirror? If you have a mirror which is like a rigid analytic object, will this be a condition that says that the intersections are some kind of aphenoids or
It's like normal course.
Or it's like normal code?
Yeah.
I mean, this is just the local description of toric picture, corner of toric picture.
You can also think it's also sort of non-compact analog of this integral system. Okay, so if you have this definition, it's very easy to check that all the multiple intersections are Liouville sectors. If you have this, because you just have the local coordinates exactly to prove that. Okay, so I think this example is almost completely trivial given a definition. The example is a cotangent bundle, as long as the boundaries are transversed to each other. If you have a covering of Q with manifolds which boundaries are mutually transverse, then the covering of the cotangent bundle is sectorial in this sense. Okay, so as I said at the beginning, cotangent bundles are essentially completely understood. Their ramified categories are completely understood. So this is not the real interesting case, but it's at least a good example to understand what the definitions are saying. so now we have a sectorial covering. We can ask whether this map is an equivalence. So we can ask whether this is this push-up these categories. Okay, so this is, we don't know how to prove this for arbitrary sectorial coverings. We know how to prove it when everything is Weinstein. So if you have a covering, there are lots and lots of things you might ask to be Weinstein, and we're going to ask for all of them to be Weinstein. So I guess first of all, you could ask for each of these regions that you get cut up into, for each of these to be Weinstein. So each of these is a LIVO manifold. Well, each of these is a LIVO sector. You can sort of complete along the boundary. You get a LIVO manifold, you ask for it to be Weinstein. You need a little bit more. You need all of the strata to be Weinstein. So this stratum here, this stratum here, everything of this form should be Weinstein. So that's basically these manifolds appear in the
What about links of strata?
Links of strata.
Or are those Weinstein automatic?
The link of a stratum. Not sure exactly what the link would be, but if you assume all of these things are Weinstein, then basically anything else you could ask about is also Weinstein because it's good other things. That's Weinstein. So if you have a sectorial covering which has this Weinstein assumption, then the Revalski category satisfies descent. Okay, so I'm not going to talk about the proof of this theorem. What I want to talk about is how can we reformulate it as a Cauchy property? How can we define a category, a topology on that category, and the Revalski category as a functor on that category, so that the statement becomes a statement that the Revalski category is a Cauchy. So this I would call a descent statement, a statement about a particular cover, and I want a statement about all the covers in a certain topology. Okay. Yeah. So the problem with just saying, okay, my topology is LIVO sectors, sectorial coverings, and that's that. The problem is that a pair of sectorial coverings need to have a common refinement, and in any sheaf theoretic context where you have a topology, this is a basic fundamental property. Any two coverings in a topology need to have a common refinement, and the reason a pair of sectorial coverings need not have a common refinement is just because, well, the notion of a sectorial covering is invariant under symplectomorphism. So if I take this sectorial covering, so imagine this is the zero section S1, and this is glued to that, and my sectorial covering is by tangent bundle of intervals. Then I can apply some compactly supported symplectomorphism and get some covering which looks like that, and do a section of, say, this one. With that one, it's not going to contain any of those.
You want to construct the Cauchy on the core.
On the core, yeah. I'm just so this is just if you just took this result and tried to make the most naive assertion about it, what it might be a Cauchy Van, you might think it's this. It's not. Yeah. So how do we get to the core? So I want to modify the notion of a LIVO sector in two ways. So the first, I want to require semiconic LIVO sector. So semiconic just means the positive LIVO flow is defined for all time. So this is a good property because it means but the it's close to an intersection. If I have two things which are semiconic, then the intersection is semiconic. It might not be a Liouville sector, but at least it's semiconic.
So does that mean the Liouville flow is tangent to the boundary?
Or going inside?
Okay, so all it means is that it's somehow it doesn't point outward on the boundary. Okay, so here's the Liouville sector. The vector field is tangent to the boundary near infinity, and the compact part it can go in or out, and that's okay. But semiconic says it always has to go in. So it's easier to understand this definition when I talk about semiconic Liouville subsector of something. So let's talk about let's draw a cotangent bundle of the sphere. Okay, so, sorry, this is a cotangent bundle of S1. That's the zero section. But I don't want the usual. Liouville vector field. I want to perturb it to make it Weinstein. So there'll be an index 0 critical point here and index 1 critical point here. The vector field. The vector field does that. Drawing a few more vectors, but I think you get the idea. So what does a semiconic Liouville subsector of this look like? So one semiconic Liouville subsector, well, okay, here's an easy way. I just take a point off the core, I look at the ball around it, and I flow it up. That's some positive flow in the Liouville flow. So that's a semiconic thing inside here. The Liouville vector field is sort of going in on this part of the boundary, and this part is tangent. And I could do this with the ball anywhere. I could take this ball here, and then the semiconic closure, right, just adds. Oh, so here's an easier example. If I have a cotangent bundle of the cotangent bundle of a submanifold. The base is also a semi. Okay, so the problem here is that most points don't have semiconic Liouville sector neighborhoods. So I want to explain this. The next example is exactly what I've written here. So this is T star S1 with this Liouville form, which is the canonical Liouville form on a cotangent bundle, perturbed by Morse function on S1 with two non-degenerate critical points. So that's exactly what I've drawn here. So this is a Weinstein, a 1-0 handle, 1-1. So this, the index 1 critical point has a small semiconic Liouville sector neighborhoods. That's what I just drew here. You take the ball, you flow it up, you get Liouville sector. The point off the core also has this nice neighborhood. This is also a Liouville sector. It's a half plane. You can see that's a Liouville sector. Okay, but the other points don't. The other points on the core don't have semiconic Liouville sector neighborhoods, right? Because if let's draw them. So if I start with this point and take a small ball and flow up under the Liouville flow, what do I get? So this flows here. This flows here. And I don't, so I get everything on this side of this fiber, the co-core of the index 1 critical point, but I don't, I don't get that fiber. It's not closed, it's open. Okay, so that is not a Liouville sector in the strict sense. It's what we call an open Liouville sector. So an open Liouville sector. Now, to specify an open Liouville sector, I specify not one manifold, but I specify two manifolds. So X is an exact symplectic manifold like before, and I also specify a contact manifold, which I call boundary infinity X. And this is bad notation because boundary infinity X does not depend on X. It's an extra piece of data. Okay, so what's going on? So I'm drawing X, and this is boundary infinity X. We have the Liouville flow. But this boundary infinity X does not have to cover all ways of going to infinity. And what we require here is that this pair should be an infinite ascending union of Liouville sectors. So for example, in this example, maybe I draw this curve and look at the complement of this. And if that's a Liouville sector, I'm good. I draw a smaller neighborhood of this part that I removed. This is also a Liouville sector. This is also a Liouville sector. Then it's an ascending union of Liouville sectors, so there's an open. So let me go back to this example here. This blue region I drew is another open Liouville sector.
So this D omega D infinity X doesn't have to be compact.
Does not have to be compact. Yeah, it can be non-compact. Yeah. Yeah. So there's no, and there's no boundary allowed. Yeah. And that's an advantage. It's more general. If you had something with boundary, just delete the boundary to get something without boundary. So let me argue that this blue object is an open Liouville sector. Well, you just exhaust it by cotangent bundles of intervals. Take something like this and let this approach this blue region, which is not there, and let this approach this blue boundary here. Okay. And these Liouville sectors which exhaust don't have to be semiconic. That's sort of the key. Okay, so the example is a cotangent bundle of any manifold, not necessarily compact. Just exhaust your manifold by compact manifolds with boundary. Exhaustion at this point by Liouville sectors. Okay, so now I want to consider the following category: semiconic open Liouville sectors, morphism which strictly preserve the Liouville flow. So now let's see, did I write it? The Rev-Chi category. I didn't. The Rev-Chi category is a functor from this category. So maybe I'll write Rev-Chi category. That's essentially a rephrasing of what I already said. Rev-Chi category is a functor from semiconic open Liouville sectors to A infinity categories. That's how many times.
Sorry, the open condition and the semiconical condition, they don't interact in any way except they're just separate conditions that we impose.
Yes. Yeah.
Just the flow is common for the two, but there is no.
Yeah. Yeah. They're separate. Yeah. If you're open, then being semi-conic, yeah, just means you're complete in the positive direction. Yeah. Just separate conditions. Yeah, I mean, so they serve different reasons. So the reason for imposing semi-conicness is so that your open sets have intersections which are still of the same sort of class or reasonable, and imposing openness is because that when you flow things up, well, you get these things which are just slightly more exotic than the ordinary mutual sectors. Okay, so what class of covers are good? So I call it a cover open Liouville sectors, Weinstein sectorial. And you can exhaust. So each of these guys xi are open Liouville sectors, and so they're exhausted by Liouville sectors. The covering is Weinstein sectorial when you can choose those exhaustions simultaneously, so that the cover that they form a Weinstein sectorial cover. Okay, so this cotangent bundles is Weinstein sectorial. So this is a you can observe this is a nicer statement than my previous statement. So in the case of Liouville sectors where you have boundary, I said, well, okay, you take a closed manifold and then you take a covered by compact manifolds with boundary and then smooth boundary, and the boundary has to intersect transversely. All the boundaries of all the sets have to intersect transversely. Here it's just any manifold and any open cover. So it's a nicer statement. Okay, and you have descent for these open covers, and this is simply a rephrasing of the earlier result. Each of you take sectorial descent for this cover, and then you let J go to infinity, the route for and you get this statement. So we want this category here to have a Grothendieck topology on it, in which we assert that that this functor is a Cauchy. Now, of course, we've only proven descent under these Weinstein assumptions, so it can't just be it's always a Cauchy. We need some hypothesis. Okay, so basically the most general context in which you can talk about sheaves is that of a Grothendieck topology. So let's review what that is. So you have a category, and we have an object of the category. So a sieve tells you which maps to X are small, or which maps to X have small image. So if a map B to X has small image, and you precompose it with a map from A to B, then A to X better also have small image, because it has smaller image. So that's the definition of a sieve. A sieve is any collection of isomorphism classes of things mapping to X with this property. So it measures smallness. So a sieve on Rn is all maps to Rn which have diameter at most 1. That's a sieve. Or all maps to Rn which have image contained in the positive half space. That's a sieve. Okay. Now if you have a sieve on, say, a topological space, you can ask, is there an open covering of that topological space where each of the open sets in my open covering belong to that sieve? And so if you have a topological space, I can tell you whether your sieve is a covering sieve or not. Okay, and that's all you need. That data of which sieves are covering sieves and which sieves are not is what you need to define the notion of a sheaf. And they have to satisfy a few axioms. So those are the axioms of a Grothendieck topology. The Grothendieck topology just tells you, for every object of your category, which sieves on that object are covering sieves. So you need these three axioms. Sieve of all maps should better be a covering sieve. The pullback of any covering sieve better be covering sieve. And being a covering sieve better be a local property. Right, so we want to ask, is there a nice rotating topology on this category? Semi-conic open Liouville sectors. Okay, so covering just means covering in the usual sense. Now, actually, I don't know what happens if you consist on only covering the core. That might be there are actually two possible things you could ask. Maybe you want to only cover the core. But I'll just leave that as a question for now. So warning about coverings in this sense. We're used to thinking about, let's say, locally compact Hausdorff topological spaces. And for those, arbitrarily fine coverings contain arbitrarily small neighborhoods of every point. But it's not true in a semi-conic topology, because in a semi-conic topology it's wildly non-Hausdorff. So if I take this cotangent bundle and take like really fine covering at the base, so I get these things covered by cotangent bundle. That's an arbitrarily fine covering in the semi-conic topology. Even though for a point here, an arbitrarily small neighborhood that looks like this, and those are not here. So, what is this a rotating topology or not? So, spoiler alert. The identity axiom and the locality axiom are trivial for this topology, but the pullback axiom is not. Why is the pullback of a cover? And basically the point is that no one promises you that you have any non-trivial covers at all, non-trivial covers by open Liouville sectors. You have plenty of covers by semi-conic open sets, but no one promises you that they're Liouville sectors. So you don't know how fine of a cover you can get in this sense. So you can turn that defect into a definition. So in order to have a rotating topology, we need this property. We need a class of semi-conic open Liouville sectors with the property that for every cover by semi-conic open sets, that you can refine that to a cover by semi-conic open Liouville sectors. Okay, I call locally sectorial, I call a semi-conic open Liouville sector locally sectorial if it belongs to this largest class with this property. So it's sort of hard to see that there is such a largest. Okay, it's not entirely obvious that there is such a largest class. I could say, well, okay, to call a Liouville sector locally sectorial when every covering by semi-conic open sets has been refined into a covering by semi-conic open Liouville sectors, and that's locally sectorial. Well, the problem is no one promises you that the open sets in the covering are again of the same class, themselves have coverings of arbitrarily defined coverings by Liouville sectors. So you have to make an inductive definition. So for every ordinal, you can consider alpha locally sectorial, where that means you have a covering, you have arbitrarily defined coverings by semi-conic Liouville sectors, which are alpha prime locally sectorial for each smaller ordinal. And there are more ordinals than there are any other. Well, the ordinals aren't a set. There are more ordinals than any set, than the elements of any set. And so eventually this notion is stable, independent of the ordinal, and that's this largest class of locally sectorial.
Is it possible to work with this definition? How check this every cover and blah blah blah? It looks impossible to work with such a definition.
To check the condition.
Yeah.
So that's what one needs to prove.
Yeah.
In fact, you need something a little bit stronger because you need Weinstein coverings. There's some. I think it probably can be proven that sort of Weinstein manifolds are in this class. That's what we want to prove, but we haven't proven that. Okay, so now we have a hypermotive topology. We can ask the question: is this a sheaf? So of course the answer is we can't prove it without some Weinstein assumptions. So this is so we need a better covering axiom. So the class of Weinstein separable semiconical primeval sectors is the largest class, such that you have arbitrarily fine covers which are Weinstein separable. Which are Weinstein sectorial cover by semiconical primeval sectors. So the proof that this exists is the same as on the previous slide. It's clearly a stronger condition. And okay, this is again a rephrasing of our result. The graph for that category is a co-sheaf in this category. So there's some trivial lemma in sheaf theory which says that to verify something is a sheaf, you just have to verify it for some class of covers which are arbitrarily fine. And it's true for the Weinstein sector. It's for the Weinstein sectorial coverings, and those are by definition arbitrarily fine. Okay, so this is the real question: which semiconical primeval sectors are Weinstein separable? And this is where I'll stop, because we don't really have an answer other than some expectations. So at least cotangent bundles are Weinstein separable because they have arbitrary. You can cover them by cotangent bundles of open subsets of the base, and those are in the same class. And those coverings are Weinstein sectorial. And we expect that Weinstein separability is preserved under attaching Weinstein handles and removing an isotropic submanifold from the contact boundary. I should have said this notion of open Liouville sector gives you a nice way of talking about this partial wrapping of the Liouville category. If you want to wrap your Lagrangian submanifolds in the complement of an isotropic submanifold of the contact boundary, you just remove that submanifold. That's an open Liouville sector.
Questions, comments?
Yeah, go ahead.
Okay, you can just, it's very understand that what you're struggling last 20 minutes is you have this nice theory profile that covering this whole transversality. You just want to put kind of put in the science quadratic topology.
In the classical notion of capacity, how does it enter this picture? Can you get some more categorical information out of it?
Capacity, like symplectic?
Yeah.
Symplectic capacities. I don't know how they interact. I mean, to talk about capacities on Liouville manifolds, you need to talk about Liouville domains, and then you have these two pieces of the boundary. I'm not sure how one should talk. I don't know how to leverage the Liouville sector condition to create a theory other than just regarding all boundaries the same. Liouville domains.
So also you have a student that use some properties of the core to connect with the generation time or dimension of the category. I mean, actually with the dimension of the category.
Yeah.
Do you know how to try to connect other generation times to this category? Yeah, go ahead.
I have a question. So, suppose you did the wrap criteria. Currently is defined as the coordinate of the wrapping. So the object, the limiting object you draw by wrapping this fiber is like a helix. But I think you can directly define the flow complex using this helix by intersecting classes. So this is kind of defined in new kind of category which involves new collection of Lagrange.
all I can do is sort of repeat things I've heard. I mean, if your Lagrangian somehow have appropriately bounded geometry, then you should be able to define for homology and the category. It's a little bit unclear how to wrap things. What if you have if you have something which is
You don't need to wrap.
you don't.
Because you choose the plurals alone.
Yeah.
Can I comment about this? You can do whatever you want, add
Can
whatever
you move
objects
up
you
a
want.
little bit so that we can...
But, you can add whatever objects you want, but the point is, I mean, it's never you're never actually going to succeed in making the category bigger, for the reason that as long as the diagonal in the product gives you the diagonal bimodule, then somehow, since the diagonal is already generated by these kind of objects, then it follows that whatever new thing you added actually is already generated by this.
For example, if you try to define category on the real dimension infinite time, then it's certainly
Any more questions? Let's thank John again.